Tonight, we're embarking on a gentle journey through space and time, exploring the fascinating story of asteroids, those ancient wanderers that have silently accompanied our planet through billions of years of cosmic history. So settle in, get comfortable, and let's drift together through the vast expanse between Mars and Jupiter, where millions of rocky worlds tumble through the darkness, each one holding secrets from the very birth of our solar system. As you close your eyes and let your breathing slow, imagine yourself floating peacefully above Earth, looking out into the infinite darkness punctuated by countless points of light. Among those lights, invisible to our eyes but ever present, are the asteroids, rocky remnants from a time before planets, before life, before anything we know existed. Tonight, we'll explore their entire story, from their violent birth in the swirling disk of dust and gas that became our solar system, to their role in shaping life on Earth, to their potential future as stepping stones for humanity's expansion into the cosmos. The story of asteroids is really the story of discovery, of human curiosity reaching out into the darkness and finding worlds we never imagined. It's a story of cosmic collisions and gentle drifts through space, of missions that have touched these ancient rocks and brought pieces of them home to Earth. And perhaps most remarkably, it's a story that's still being written, with new chapters added every time we point our telescopes toward the sky or send our robotic explorers out to meet these celestial neighbours. Long before we knew what asteroids were, before we even had a word for them, humans looked up at the night sky and noticed that while most stars remained fixed in their celestial patterns, some lights wandered among them. The ancient Greeks called these wanderers planetes, from which we get our word planet. They identified 5 of these wandering stars, Mercury, Venus, Mars, Jupiter, and Saturn, and wove them into their mythology and understanding of the cosmos. But between Mars and Jupiter, in a region of space that seemed strangely empty, there were mysteries yet to be discovered. Ancient Chinese astronomers, meticulous in their observations, recorded what they called guest stars, temporary visitors to the night sky that would appear and disappear. While many of these were comets or novae, some observations remain unexplained and might have been particularly bright asteroids passing close to Earth. In ancient Babylon, astronomers created detailed charts of planetary movements, noting with mathematical precision where each wandering star would be on any given night. They too noticed something curious about the spacing of the planets. There seemed to be too large a gap between Mars and Jupiter, as if something was missing. Indigenous peoples around the world had their own relationships with the night sky, seeing in its patterns the stories of their ancestors and guides for navigation and timekeeping. The Aboriginal Australians, whose astronomical traditions stretch back tens of thousands of years, speak of the Emu in the sky, a dark constellation formed by dust clouds in the Milky Way. They understood that the sky was not just distant lights, but a 3-dimensional space through which objects moved, some closer, some farther away. While they didn't specifically identify asteroids, their sophisticated understanding of celestial mechanics laid groundwork for thinking about objects moving through space at different distances and speeds. In medieval Europe, astronomers working within the framework of Aristotelian cosmology believed the heavens were perfect and unchanging. The sphere of fixed stars was thought to be the outermost boundary of creation, with the planets moving in perfect circles within crystal spheres. This worldview left no room for asteroids. Chunks of rock tumbling chaotically through space didn't fit the model of divine perfection. Yet even then, careful observers noted things that didn't quite fit. Tycho Brahe, observing a supernova in 1572, proved that changes could occur in the supposedly immutable heavens. His meticulous observations of planetary positions, later inherited by Johannes Kepler, would eventually help reveal that planetary orbits were ellipses, not perfect circles, a discovery that would prove crucial for understanding asteroid orbits centuries later. The invention of the telescope in the early 1600s opened new windows into the cosmos. Galileo Galilei, turning his primitive telescope toward Jupiter in 1610, discovered 4 moons orbiting the giant planet. The first objects discovered that clearly orbited something other than Earth. This discovery shattered the geocentric model and showed that the solar system was far more complex than previously imagined. As telescopes improved, astronomers began mapping the sky with unprecedented precision, cataloguing stars and tracking planetary movements with ever greater accuracy. By the late 1700s, astronomers had noticed a curious mathematical pattern in the distances of planets from the Sun. Johann Daniel Titius first noted this pattern in 1766, but it was Johann Elert Bode who popularized it in 1772, leading to it being called the Titius-Bode law. This empirical rule suggested that planetary distances followed a simple mathematical progression. Mercury, Venus, Earth, Mars, Jupiter, and Saturn all fit the pattern reasonably well, but there was a glaring gap. According to the law, there should be a planet between Mars and Jupiter at about 2.8 astronomical units from the Sun. This missing planet became an obsession for astronomers of the late 18th century. The discovery of Uranus by William Herschel in 1781, at a distance that matched the Titius-Bode prediction remarkably well, only intensified the search. Surely, astronomers reasoned, if the law predicted Uranus correctly, the missing planet between Mars and Jupiter must exist. Baron Franz Xaver von Zach, a Hungarian astronomer, went so far as to organize a group of 24 astronomers across Europe in 1700, calling them the Celestial Police, with each member assigned a 15-degree section of the zodiac to search for the missing planet. But the discovery, when it came, was made by someone outside this organised search. On the first night of the 1800s, January 1st, 1801, Giuseppe Piazzi, a Catholic priest and astronomer working at the Palermo Observatory in Sicily, was creating a star catalogue when he noticed something unusual. A faint star in the constellation Taurus wasn't where it should be. The next night it had moved. Piazzi initially thought he had discovered a comet, but this object showed no sign of a comet's characteristic fuzzy coma or tail. It was a point of light, like a star, but it moved against the background stars, like a planet. Piazzi tracked his discovery for several weeks before illness forced him to stop observations. By the time he recovered, the object had moved too close to the Sun to be observed. He had managed to track it for only about 3 degrees of its orbit, not nearly enough to calculate its full orbital path with the mathematical techniques of the day. The object Piazzi had found seemed lost to the glare of the Sun, perhaps forever. Enter Carl Friedrich Gauss, a young German mathematician who had been developing new techniques for calculating orbits from limited observations. Using Piazzi's data, Gauss employed his method of least squares, a revolutionary mathematical technique he had invented to predict where the object would reappear when it emerged from the Sun's glare. His calculations proved remarkably accurate. On December 31st, 1801, almost exactly a year after Piazzi's initial discovery, Baron von Zach relocated the object within half a degree of Gauss's predicted position. Piazzi named his discovery Ceres Ferdinandea, after the Roman goddess of agriculture and King Ferdinand of Sicily, though the royal name was later dropped. Ceres appeared to be the missing planet predicted by the Titius-Bode law, orbiting at 2.77 astronomical units from the Sun, remarkably close to the predicted 2.8. The astronomical community celebrated. The solar system was complete, the pattern confirmed. But the celebration was premature. On March 28, 1802, Heinrich Olbers, a physician and amateur astronomer in Bremen, Germany, discovered another object in the same region of space. He named it Pallas, after Pallas Athena, the Greek goddess of wisdom. This was puzzling. Why would there be two planets where the Titius-Bode law predicted only one? And both Ceres and Pallas seemed remarkably small compared to the other planets. William Herschel, observing these new discoveries with his powerful telescopes, noted that, unlike planets which showed visible disks when magnified, these objects remained point-like, similar to stars. He proposed a new term for these objects, asteroids, from the Greek words meaning star-like. The discoveries continued at an accelerating pace. Carl Ludwig Harding found Juno in 1804, and Olbers discovered a second asteroid, Vesta, in 1807. It was becoming clear that instead of a single missing planet, the space between Mars and Jupiter contained multiple small bodies. The neat picture suggested by the Titius-Bode law was giving way to something far more complex and interesting. For several decades after the discovery of Vesta, no new asteroids were found. The four known asteroids, Ceres, Pallas, Juno and Vesta, were often still referred to as planets in astronomical texts of the early 19th century. But this changed dramatically in 1845 when Carl Ludwig Henke, an amateur astronomer who had been searching for 15 years, discovered a fifth asteroid, Astrea. The floodgates opened. By 1850, 13 asteroids were known. By 1868, the number had reached 100. By the end of the 19th century, over 400 asteroids had been discovered. This explosion in discoveries was aided by several technological advances. The development of stellar cartography, detailed star maps, made it easier to spot objects that didn't belong. More importantly, the introduction of astrophotography in the 1890s revolutionized asteroid hunting. Max Wolf pioneered the use of photographic plates to discover asteroids. By taking long exposure photographs of the same region of sky, asteroids would appear as short streaks against the stationary stars, making them easy to identify. Wolf himself discovered over 200 asteroids using this technique. As the number of known asteroids grew into the thousands, astronomers realized they were dealing with a population of objects unlike anything else in the solar system. These weren't failed planets or fragments of a destroyed world, as some early theories suggested. They were something else entirely, leftover building blocks from the solar system's formation, preserved in the deep freeze of space for over 4 billion years. What asteroids really are, composition and classification. To truly understand asteroids, we need to journey back 4.6 billion years, to a time before Earth existed, before the Sun had fully formed, when our entire solar system was nothing more than a vast, slowly rotating cloud of gas and dust floating in interstellar space. This solar nebula, as astronomers call it, was composed primarily of hydrogen and helium gas, but crucially, it also contained tiny solid particles, grains of dust made of silicon, carbon, iron, and other heavier elements, forged in the hearts of dying stars that had exploded long before our sun was born. Picture this primordial cloud, spanning a region of space perhaps 2 light years across, slowly collapsing under its own gravity. As it contracts, it begins to spin faster, like a figure skater pulling in their arms. The cloud flattens into a disk, with most of the material falling toward the center, where temperatures and pressures rise until nuclear fusion ignites, giving birth to our sun. But not all the material falls into the center. Some remains in the disk, orbiting the young star. In this swirling disk of dust and gas, something remarkable begins to happen. The dust grains, no larger than particles of smoke, begin to stick together. At first the binding is weak, just electrostatic forces and van der Waals forces holding the particles together. But as these fluffy aggregates grow larger, gravity begins to play a role. The process is called accretion, and it's how all the solid bodies in our solar system formed. Close to the young sun, where temperatures are high, only materials with high melting points can remain solid. Things like iron, nickel, and rocky silicate minerals. Water, methane, and ammonia exist only as gases here. Further out, beyond what astronomers call the frost line or snow line, located at about 3 astronomical units from the Sun in our early solar system, temperatures are cold enough for these volatile compounds to freeze into solid ice. This fundamental division explains why the inner solar system is dominated by rocky planets, while the outer solar system contains gas and ice giants. In the region where asteroids now reside, between about 2 and 4 astronomical units from the Sun, conditions were particularly interesting. The area straddled the frost line, meaning that asteroids forming in the inner part of the belt would be rocky and dry, while those forming further out could incorporate significant amounts of ice. This is exactly what we observe today in the composition of different asteroid types. But here's where the story takes a dramatic turn. In most parts of the disk, the growing planetesimals, bodies ranging from meters to hundreds of kilometers across, continue to collide and merge, eventually forming planets. But in the asteroid belt region, something prevented this process from completing. That something was Jupiter. Jupiter, the giant of our solar system, formed early and quickly. Within just a few million years of the Sun's birth, Jupiter had grown to roughly its current size, over 300 times the mass of Earth. Its immense gravity had profound effects on the rest of the forming solar system, particularly on its inner neighbour, the asteroid belt region. Jupiter's gravitational influence stirred up the orbits of planetesimals in what would become the asteroid belt, increasing their relative velocities. Instead of gently merging when they encountered each other, these bodies now collided with such violence that they shattered rather than stuck together. Imagine 2 large asteroids, each perhaps 100 kilometers across, approaching each other in space. In the inner solar system, where planetary formation was proceeding normally, such bodies would typically be moving relatively slowly with respect to each other, perhaps a few meters per second. At such speeds, their mutual gravity could pull them together, and even if they collided, the impact would be gentle enough that they would likely stick together. But in the asteroid belt, with Jupiter's gravity pumping up orbital eccentricities and inclinations, these same bodies might approach each other at speeds of several kilometers per second. The collision would be catastrophic, shattering both bodies into countless fragments. This process, called dynamical excitation, effectively halted planet formation in the asteroid belt. Instead of growing into a planet, the material remained as a swarm of smaller bodies. Computer simulations suggest that the original asteroid belt might have contained as much mass as Earth or more, but gravitational perturbations from Jupiter ejected most of this material from the solar system or sent it spiraling into the Sun. What remains today, the entire current asteroid belt, has a combined mass of only about 4% of our Moon. As we study asteroids today, we see clear evidence of this violent history written in their very structure and composition. Let's explore the main types of asteroids and what they tell us about the conditions in which they formed. C-type asteroids, or carbonaceous asteroids, are the most common type, making up about 75% of known asteroids. These dark, carbon-rich bodies are found predominantly in the outer regions of the asteroid belt, beyond about 2.7 astronomical units from the Sun. Their surfaces are extremely dark, reflecting only about 3 to 5% of the sunlight that hits them, darker than coal. This low reflectivity, or albedo, comes from the carbon compounds and organic molecules that coat their surfaces. When we analyse the light reflected from C-type asteroids using spectroscopy, breaking the light into its component wavelengths, we see absorption features that indicate the presence of water-bearing minerals, clays, and hydrated silicates. These are minerals that formed in the presence of liquid water, suggesting that many C-type asteroids experienced aqueous alteration early in their history. The parent bodies of these asteroids were large enough and formed early enough that radioactive decay could heat their interiors, melting ice and allowing liquid water to alter the original minerals. The composition of C-type asteroids closely matches that of carbonaceous chondrite meteorites found on Earth. These meteorites are among the most primitive materials in the solar system, containing minerals and organic compounds that formed in the solar nebula before the planets. Some carbonaceous chondrites contain tiny inclusions called calcium-aluminum-rich inclusions, or KIs, which are the oldest dated materials in the solar system at 4.567 billion years old. They also contain organic molecules, including amino acids, the building blocks of proteins. The Murchison meteorite, which fell in Australia in 1969, contains over 70 different amino acids, only 19 of which are found in life on Earth. S-type asteroids, or silicaceous asteroids, make up about 17% of known asteroids and dominate the inner asteroid belt, within about 2.2 astronomical units of the Sun. These asteroids are brighter than C-types, with albedos typically between 10 and 22%, giving them a slightly reddish colour. They're composed primarily of silicate minerals mixed with metallic iron and nickel. Spectroscopic observations of S-type asteroids reveal absorption features consistent with minerals like olivine and pyroxene, the same minerals that make up much of Earth's mantle. These asteroids appear to be the source of ordinary chondrite meteorites. The most common type of meteorite falls on Earth. The match between S-type asteroid spectra and ordinary chondrite spectra wasn't immediately obvious because space weathering, the bombardment of asteroid surfaces by solar wind particles and micrometeorites, alters the optical properties of the surface. It took detailed laboratory experiments and observations by spacecraft to confirm the connection. Many S-type asteroids show evidence of thermal metamorphism, heating that altered their mineral structure but wasn't intense enough to cause complete melting. This heating likely occurred early in solar system history when radioactive isotopes like aluminum-26 were still abundant. The decay of these short-lived isotopes could heat asteroid interiors to temperatures of several hundred to over 1,000 degrees Celsius, causing minerals to recrystallize and driving off volatile compounds. M-type asteroids, or metallic asteroids, are relatively rare, making up only about 8% of known asteroids. These asteroids have moderate albedos and spectra that suggest surfaces rich in metallic iron and nickel. For many years, astronomers believed M-type asteroids were the exposed metallic cores of differentiated planetesimals, bodies that had grown large enough for heating to cause melting and separation into a metallic core and rocky mantle similar to Earth's structure. Subsequent collisions were thought to have stripped away the rocky mantle, leaving the metallic core exposed. This picture has become more complex as we've studied M-type asteroids in greater detail. While some, like asteroid 16 Psyche, do appear to be largely metallic and may indeed be exposed cores, others show evidence of silicate minerals on their surfaces. Some M-type asteroids might be more like iron-rich chondrites rather than pure metal. The NASA Psyche mission, which launched in October 2023 and will arrive at asteroid Psyche in 2029, aims to study what may be an exposed planetary core up close, potentially giving us insights into the normally hidden metallic hearts of planets like Earth. Beyond these three main classes, there are numerous rarer asteroid types, each telling its own story about the conditions and processes in the early solar system. V-type asteroids, for example, have spectra similar to basaltic rock, volcanic lava that cooled on or near the surface of a body. These asteroids are thought to be fragments of the crust of asteroid 4 Vesta, blasted off by a giant impact that created the enormous crater near Vesta's south pole. The head meteorites, Hayabusa, Eucrites and Diogenites found on Earth are believed to come from Vesta, giving us actual samples of this differentiated asteroid. D-type asteroids are found primarily in the outer asteroid belt and among the Jupiter Trojans. They're extremely dark and red, possibly rich in organic compounds and ices. Their composition might be similar to cometary nuclei, suggesting they formed in the very cold outer regions of the solar system and were later gravitationally scattered inward. P-type asteroids are also very dark and are found in the outer asteroid belt. They show evidence of organic rich surfaces and possibly water ice. Some researchers suggest these might be captured comets that have lost their volatile ices through repeated passages near the Sun. The internal structure of asteroids varies dramatically depending on their size and history. The smallest asteroids, those less than a few hundred meters across, are likely monolithic rocks, single solid pieces, or perhaps fractured but still cohesive bodies. But many asteroids, particularly those in the kilometre to tens of kilometres size range, appear to be rubble piles, collections of rocks and boulders held together loosely by their mutual gravity. The rubble pile structure was first confirmed when the Near-Shoemaker spacecraft orbited asteroid 433 Eros. The spacecraft's detailed observations revealed that Eros, despite being about 34 kilometres long, has a density only about 2.7 grams per cubic centimetre, similar to granite. But the numerous craters and fractures visible on its surface suggested it had survived impacts that should have shattered a solid rock of that size. The explanation is that Eros is fractured throughout, with voids making up perhaps 20 to 30% of its volume. When such a body is hit by an impactor, the energy is absorbed by rearranging the rubble rather than shattering the entire asteroid. The Japanese spacecraft Hayabusa's visit to asteroid Itokawa provided even more dramatic evidence of rubble pile structure. Itokawa, only about 350 meters long, looks like two distinct lobes stuck together, covered with boulders of various sizes and patches of fine gravel. Its density is only about 1.9 grams per cubic centimetre, suggesting about 40% of its volume is empty space. Itokawa appears to be a collection of fragments from a larger body that was shattered by an impact, with the pieces later reaccumulating through gravity. Larger asteroids, those above about 100 kilometres in diameter, had different histories. Many of these bodies grew large enough for radioactive heating to cause differentiation, the separation into layers of different composition. The densest materials, primarily metallic iron and nickel, would sink to form a core, while lighter silicate minerals would rise to form a mantle and crust. Asteroid 4. Vesta, about 525 kilometres in diameter, is a prime example of a differentiated asteroid. Spectroscopic observations and meteorites from Vesta show it has a basaltic crust, an olivine-rich mantle, and likely an iron-nickel core. The largest asteroid, Ceres, now classified as a dwarf planet, represents yet another category. With a diameter of about 940 kilometres, Ceres is massive enough that its own gravity has pulled it into a roughly spherical shape, a state called hydrostatic equilibrium. Data from NASA's Dawn spacecraft, which orbited Ceres from 2015 to 2018, revealed a complex world with a differentiated interior. Ceres has a rocky core surrounded by an icy mantle that may contain more water than all of Earth's oceans. Its surface shows evidence of cryovolcanism, eruptions of water and other volatiles rather than molten rock. Bright spots in some craters appear to be deposits of salts left behind, as briny water erupted from below and sublimated in the vacuum of space. The study of asteroid composition has been revolutionized by sample return missions. The Japanese Hayabusa mission returned tiny grains from S-type asteroid Itokawa in 2010. These samples, though totaling less than a milligram, confirmed the link between S-type asteroids and ordinary chondrite meteorites and revealed details about space weathering processes that could never have been determined from remote observations alone. Hayabusa 2, which returned samples from C-type asteroid Ryugu in December 2020, brought back about 5.4 grams of material. Initial analysis of these samples has revealed fascinating insights. The material is extremely primitive, matching the most primitive carbonaceous chondrite meteorites. It contains abundant water-bearing minerals and organic molecules, including amino acids. Remarkably, the samples are extremely fragile and porous, with densities suggesting they're more than 50% empty space. Such material would never survive passage through Earth's atmosphere as a meteorite, meaning these samples are giving us access to a type of solar system material we've never been able to study before. NASA's OSIRIS-REx mission returned samples from another C-type asteroid, Bennu, in September 2023, delivering about 250 grams of material, the largest asteroid sample ever returned to Earth. Early analysis shows the material is rich in carbon and water-bearing minerals, with some samples containing up to 5% carbon by weight. The samples also contain sulfide minerals that would have been destroyed if they had fallen to Earth as meteorites, preserving evidence of chemical processes from the early solar system. These direct samples are invaluable because they can be studied with the full range of laboratory techniques available on Earth, including methods that haven't even been invented yet. The Apollo lunar samples, for example, are still yielding new discoveries more than 50 years after they were collected, as new analytical techniques become available. The same will undoubtedly be true for asteroid samples. The mineralogy of asteroids provides crucial clues about the temperature and chemical conditions in different parts of the forming solar system. The presence of certain minerals can indicate the maximum temperature a body experienced. For example, the mineral troilite, iron sulfide, breaks down at temperatures above about 600 degrees Celsius, so its presence indicates an asteroid never got hotter than that. The presence of phyllosilicates, clay minerals, indicates the past presence of liquid water, while anhydrous minerals suggest dry conditions. Isotopic analysis of asteroid materials provides another window into solar system history. Different isotopes of the same element can reveal where and when material formed. For example, oxygen has 3 stable isotopes, and the ratios of these isotopes vary in different parts of the solar system. By measuring oxygen isotope ratios in asteroid samples, scientists can determine whether material formed in the inner or outer solar system. Some meteorites and asteroid samples contain isotopic anomalies, unusual isotope ratios that suggest the inclusion of pre-solar grains, actual stardust that predates our solar system. The organic molecules found in asteroids are particularly intriguing. Carbonaceous asteroids contain a complex suite of organic compounds, including amino acids, nucleobases, components of DNA and RNA, and sugar-related compounds. These molecules, formed through non-biological processes, in the cold depths of space or in the warm, wet interiors of asteroid parent bodies. The delivery of such molecules to early Earth by asteroid and comet impacts may have provided the raw materials necessary for the origin of life. The water content of asteroids has important implications for both solar system history and future space exploration. Many C-type asteroids contain 10 to 20% water by mass, locked up in hydrated minerals. Some may contain ice in their interiors. This water formed from ice that condensed in the outer asteroid belt and beyond, where temperatures were cold enough for water to freeze. The presence of hydrated minerals in asteroids that now orbit in the inner asteroid belt indicates that significant mixing occurred in the early solar system, with material forming in different regions being scattered across the belt. The asteroid belt, a cosmic highway. Between the orbits of Mars and Jupiter lies a vast region of space that captures the imagination. The asteroid belt, often depicted in science fiction as a dense field of tumbling rocks that spacecraft must carefully navigate through. The reality is both more subtle and more fascinating. The asteroid belt is less like a cosmic obstacle course and more like a sparsely populated desert with vast distances between individual asteroids. Yet within this seemingly empty space lies a complex dynamic system that preserves the history of our solar system's formation and continues to evolve today. The asteroid belt extends from about 2.1 to 3.3 astronomical units from the Sun, though its boundaries are not sharp and asteroids can be found both closer to and farther from the Sun. To put this in perspective, the inner edge of the belt is about 200 million kilometers from the Sun, while the outer edge is nearly 500 million kilometers away. This is an enormous volume of space. If you were to take a journey from the inner edge to the outer edge of the belt, travelling at the speed of a typical commercial jetliner, it would take you over 40 years to complete the trip. Within this vast region, asteroids are not distributed uniformly. Instead, they're concentrated in certain orbital distances and avoided in others, creating a complex structure that reflects billions of years of gravitational sculpting, primarily by Jupiter. The total mass of all asteroids in the belt is surprisingly small, about 4% of the Moon's mass, or about 3 times 10 to the 21st kilograms. If you could gather all the asteroids together, they would form a body only about 1,500 kilometers in diameter, smaller than our Moon. The distribution of this mass is highly skewed toward the largest objects. Ceres alone contains about 25% of the total mass of the asteroid belt. The 4 largest asteroids, Ceres, Vesta, Pallas, and Hygiea, together account for about half of the belt's total mass. The vast majority of asteroids are small bodies less than 1 kilometer across, and while they're numerous, they contribute very little to the total mass. Despite the sparse distribution of material, the asteroid belt is far from empty or boring. It's a dynamic environment where asteroids follow complex orbital dances, occasionally colliding, sometimes being ejected from the belt entirely, and constantly being shaped by the gravitational influences of the planets, particularly Jupiter. The current asteroid belt is not a pristine remnant from the solar system's formation, but rather a highly evolved system that's been dramatically altered over billions of years. One of the most striking features of the asteroid belt is the presence of Kirkwood gaps, regions where few asteroids are found. These gaps occur at specific distances from the Sun, where an asteroid's orbital period would be in a simple integer ratio with Jupiter's orbital period. For example, at 2.5 astronomical units from the Sun, an asteroid would orbit the Sun exactly 3 times for every 1 orbit of Jupiter. This is called a 3-to-1 resonance. At 2.82 astronomical units, the ratio is 5:2. At 2.96 astronomical units, it's 7:3. These resonances act like cosmic pumps, gradually increasing the eccentricity of any asteroid that wanders into them. Here's how it works. Imagine an asteroid in the 3:1 resonance with Jupiter. Every 3 orbits, it returns to the same configuration with Jupiter, experiencing a gravitational tug in the same direction. Over time, these repeated tugs add up, like pushing a child on a swing at just the right moment. The asteroid's orbit becomes more and more elliptical until it either collides with another body or gets ejected from the resonance entirely. This process has cleared out most asteroids from these resonant orbits, creating the gaps we observe today. The Kirkwood gaps divide the asteroid belt into several distinct regions, each with its own characteristics. The inner belt, from about 2.1 to 2.5 astronomical units, is dominated by S-type asteroids, rocky bodies with surfaces rich in silicate minerals. This region includes many of the asteroid families we'll discuss shortly. The Flora family, for instance, occupies much of the inner belt and may be the source of many of the meteorites that fall to Earth. The middle belt extends from about 2.5 to 2.82 astronomical units, bounded by the 3:1 and 5:2 resonances with Jupiter. This region contains a mix of S-type and C-type asteroids. Some of the most interesting asteroids reside here, including Vesta, the brightest asteroid and the only one occasionally visible to the naked eye from Earth. The outer belt, from 2.82 to about 3.3 astronomical units, is dominated by C-type asteroids, dark carbon-rich bodies that may contain significant amounts of water ice. The transition from S-type dominated to C-type dominated regions roughly corresponds to the location of the ancient frost line in the solar nebula, beyond which water could condense as ice. This preserved gradient in asteroid composition provides a fossil record of temperature conditions in the early solar system. Beyond the main belt, we find several special populations of asteroids. The Cybele asteroids orbit between 3.3 and 3.7 astronomical units, in the gap between the main belt and the 2:1 resonance with Jupiter. Even farther out, between 4.6 and 5.4 astronomical units, we find the Hilda asteroids. These asteroids are in a 3:2 resonance with Jupiter, but unlike the destabilizing resonances that create the Kirkwood gaps, this resonance is stable. The Hilda asteroids form a dynamic triangular pattern that rotates as Jupiter orbits the Sun. Let's explore some of the major asteroids that call the belt home, each with its own unique story to tell. Ceres, the giant of the asteroid belt, deserves special attention. Discovered on the first day of the 19th century, Ceres was initially hailed as the missing planet between Mars and Jupiter. Today, it's classified as a dwarf planet, the only one in the inner solar system. With a diameter of about 940 kilometers, Ceres is large enough that its gravity has pulled it into a nearly spherical shape, unlike the irregular shapes of smaller asteroids. When NASA's Dawn spacecraft arrived at Ceres in March 2015, it revealed a world far more complex than anyone had imagined. The surface is heavily cratered, as expected for an ancient body, but it also shows signs of recent geological activity. Ahuna Mons, a 4-kilometre-high mountain, appears to be a cryovolcano, a volcano that erupts water, ammonia, and other volatiles instead of molten rock. Its smooth flanks and well-defined shape suggest it formed relatively recently in geological terms, perhaps within the last few 100 million years. The most striking features on Ceres are the bright spots that puzzled scientists when Dawn first approached. The largest of these, in a Carter crater, turned out to be deposits of sodium carbonate and other salts. These appear to have been deposited by salty water that erupted or seeped from beneath the surface and then sublimated away in the vacuum of space, leaving the salts behind. The presence of these salts, along with other evidence, suggests that Ceres harbours a briny ocean beneath its icy crust, making it potentially habitable for microbial life. Ceres rotates once every 9 hours, and spectroscopic observations have detected water vapour emanating from certain regions of its surface. This water vapour appears when these regions face the sun, suggesting that solar heating causes ice near the surface to sublimate directly into vapour. The amount is small, about 6 kilograms per second, but it demonstrates that Ceres is an active world, not a dead rock. The interior structure of Ceres, as revealed by Dawn's gravity measurements, consists of a rocky core surrounded by an icy mantle. The mantle may contain more water than all of Earth's oceans combined. This makes Ceres a potential resource for future space exploration, a fueling station where spacecraft could replenish their water supplies for drinking, for conversion to rocket fuel, or for use as radiation shielding. Vesta, the second most massive asteroid, presents a completely different story. At about 525 kilometers in diameter, Vesta is a differentiated world with a metallic core, a rocky mantle, and a basaltic crust, similar in structure to terrestrial planets like Earth. But unlike Earth, Vesta's small size meant it cooled quickly, freezing its geology in place billions of years ago and preserving a record of the early solar system. Vesta's southern hemisphere is dominated by 2 enormous impact basins, Rhea Silvia and Venonaya. Rhea Silvia, the younger of the two, is about 500 kilometers in diameter, nearly as wide as Vesta itself. The impact that created it nearly shattered the asteroid, excavating about 1% of Vesta's total volume and launching fragments across the solar system. Many of these fragments eventually found their way to Earth as Hadea meteorites, Howardites, Eucrits, and Diogenites, giving us actual samples of Vesta to study in our laboratories. The central peak of Rhea Silvia rises 22 kilometers above the crater floor, making it one of the tallest mountains in the solar system. From its summit, you would see a horizon that curves dramatically away, reminding you that you're standing on a small world. The weak gravity, only about 2% of Earth's, means you could easily jump dozens of meters high, and a thrown rock might achieve escape velocity, never to return. Dawn's observations revealed that Vesta's surface tells a complex story of volcanic activity and impact cratering. Dark material, possibly delivered by carbon-rich impactors, is scattered across the surface. Long linear gullies, some hundreds of kilometers long, wrap around the equator, fractures caused by the massive impacts that created the southern basins. These features, called fossae, show that even solid rock can behave like a liquid when subjected to forces of sufficient magnitude. Pallas, the third most massive asteroid, is one of the most enigmatic objects in the belt. With a diameter of about 512 kilometers, it's comparable in size to Vesta, but its highly inclined orbit, tilted about 35 degrees to the plane of the solar system, makes it difficult to reach with spacecraft. No mission has yet visited Pallas, though the European Space Agency has considered it for future exploration. What we know about Pallas comes primarily from telescopic observations and a brief distant encounter by the Dawn spacecraft. It appears to be a B-type asteroid, possibly rich in water ice and organic compounds. Its density suggests a composition intermediate between rocky and icy bodies. Hubble's Space Telescope images show that Pallas is somewhat flattened, possibly due to a large impact basin near its south pole. The high inclination of Pallas's orbit means it experiences more high-velocity impacts than other large asteroids, which may explain its heavily cratered surface. These violent collisions may have prevented Pallas from differentiating into distinct layers like Vesta, instead leaving it as a more homogeneous mixture of rock and ice. Hygeia, the fourth largest asteroid, was long overlooked despite its size. With a diameter of about 430 kilometers, it's the largest member of the Hygeia family of asteroids. Recent observations with the European Southern Observatory's Very Large Telescope revealed that Hygeia is nearly spherical, potentially qualifying it for dwarf planet status alongside Ceres. Hygeia appears to be a C-type asteroid with a dark surface. Its nearly spherical shape is surprising given its size. It's right at the boundary, where objects become massive enough for gravity to overcome material strength and pull them into a round shape. The Hygeia family, which includes thousands of smaller asteroids, appears to have formed from a catastrophic collision that shattered a larger parent body. Remarkably, Hygeia itself might be the reaccumulated remains of this shattered parent body, reformed from the debris. Beyond these giants, the asteroid belt contains hundreds of thousands of smaller but no less interesting worlds. Eros, though technically a near-Earth asteroid that has been perturbed from the main belt, was the first asteroid to be orbited by a spacecraft. The Near Shoemaker mission revealed a battered, potato-shaped world 34 kilometers long, covered with craters and mysterious grooves that might be fractures from ancient impacts. Ida, a 56-kilometer-long S-type asteroid, made history in 1993 when the Galileo spacecraft discovered it has a tiny moon, Dactyl, only 1.6 kilometers across. This was the first confirmed asteroid moon, proving that asteroids could have their own satellites. Since then, hundreds of binary and even triple asteroid systems have been discovered. Gaspra, another S-type asteroid visited by Galileo, showed us that even small asteroids, it's only about 18 kilometers long, can have complex surfaces with grooves, ridges, and varied crater populations, suggesting different ages for different regions. The asteroid belt is also organized into families, groups of asteroids that share similar orbits, and are thought to be fragments from collisional breakups of larger parent bodies. These families provide insights into the collisional history of the belt and the internal structure of asteroids. The Flora family, one of the largest and innermost families, contains several thousand members and may be the source of many of the ordinary chondrite meteorites that fall to Earth. The parent body was probably a partially differentiated asteroid that was catastrophically disrupted, scattering fragments throughout the inner belt. The Eunomia family is another large family in the middle belt, notable for being relatively young, perhaps only about 100 million years old. The youth of this family means its members haven't had time to spread far from their initial orbits, making it easier to identify family members and study the dynamics of collisional breakups. The Themis family in the outer belt is particularly interesting because many of its members show evidence of water ice on their surfaces. Some Themis family asteroids have been caught in the act of sublimating, temporarily developing comet-like tails. These main belt comets, or active asteroids, blur the traditional distinction between asteroids and comets. The Coronis family provides evidence for a relatively recent collision about 2 billion years ago that created a cluster of asteroids with remarkably similar spectral properties, suggesting they all came from the interior of a homogeneous parent body. The dynamics of the asteroid belt continue to evolve today. Collisions between asteroids, while rare on human timescales, are ongoing. The Yorp effect, changes in rotation rate due to the uneven reflection and re-emission of sunlight, can spin asteroids up until they fly apart or cause them to tumble chaotically. The Yarkovsky effect, a tiny force caused by the delayed re-emission of absorbed sunlight, slowly changes asteroid orbits over millions of years, causing them to drift inward or outward through the belt. Some asteroids are on unstable orbits that will eventually lead them out of the belt entirely. They might be thrown into the inner solar system to become near-Earth asteroids, or ejected to the outer solar system or beyond. Others are gradually grinding themselves to dust through collisions, contributing to the zodiacal light, the faint glow visible in the night sky caused by sunlight reflecting off interplanetary dust. The asteroid belt also contains some truly unusual objects that challenge our understanding. Chariklo, though technically a centaur orbiting between Saturn and Uranus, was discovered in 2013 to have two thin rings, the first asteroid known to have rings. This discovery was completely unexpected and showed that rings aren't limited to giant planets. Psyche, a 220-kilometre diameter M-type asteroid, appears to be largely metallic and may be the exposed core of a protoplanet that lost its rocky mantle in ancient collisions. NASA's Psyche mission, currently en route, will study this unique object up close, potentially giving us our first look at a planetary core. Some asteroids show evidence of past or present activity that seems more comet-like than asteroidal. Ceres occasionally vents water vapour. Phaethon, the parent body of the Geminid meteor shower, develops a dust tail when it passes close to the Sun, despite showing no evidence of ice. These active asteroids challenge our traditional categories and show that the distinction between asteroids and comets is not always clear-cut. The asteroid belt serves as a natural laboratory for studying planetary formation. Unlike the planets, which have been heavily processed by geological activity, many asteroids preserve material from the earliest days of the solar system. They show us what the building blocks of planets looked like before they were assembled into larger bodies. The structure of the belt also provides evidence for planetary migration in the early solar system. The current asteroid belt is too depleted in mass to have formed in its current state. Models suggest that the belt originally contained much more material, perhaps enough to form a Mars-sized planet. But as Jupiter and Saturn migrated through the solar system early in its history, Jupiter moving inward and then back outward in what's called the Grand Tack model, they would have scattered most of this material, leaving only the remnant we see today. Near-Earth asteroids are cosmic neighbours. While the main asteroid belt lies comfortably distant between Mars and Jupiter, not all asteroids stay in their cosmic lane. Some have been nudged, pulled and gravitationally scattered into orbits that bring them much closer to home. These are the near-Earth asteroids, or NEAs, wanderers whose paths cross or approach Earth's orbit, making them both scientifically valuable and potentially hazardous. They are our nearest neighbours in space beyond the Moon, and understanding them is crucial not only for planetary science, but for the future of life on Earth. A near-Earth asteroid is technically defined as any asteroid whose orbit brings it within 1.3 astronomical units of the Sun. This definition encompasses several distinct populations based on their orbital characteristics. The Oteera asteroids have orbits entirely within Earth's orbit, never venturing farther from the Sun than we do. These are the rarest NEAs, difficult to discover because they are always relatively close to the Sun from our perspective, visible only briefly during twilight. The Aten asteroids have average orbital distances less than Earth's, but with enough eccentricity that they cross our orbit. Named after 2362 Aten, discovered in 1976, these asteroids spend most of their time inside Earth's orbit, but regularly cross our path. The Apollo asteroids, named after 1862 Apollo discovered in 1932, have average distances from the Sun greater than Earth's, but cross our orbit due to their eccentric paths. These are the most numerous type of Earth-crossing asteroids. Finally, the Amma asteroids approach Earth's orbit but don't currently cross it. They come close, with orbits that bring them between 1.017 and 1.3 astronomical units from the Sun at their closest approach, but they remain outside Earth's path. However, over long timescales, gravitational perturbations can evolve armor orbits into Earth-crossing configurations. The population of near-Earth asteroids is not static, but constantly evolving. These objects didn't form where we find them today. The region near Earth's orbit was too hot during the solar system's formation for asteroids to condense. Instead, NEAs are immigrants from elsewhere, primarily from the main asteroid belt, but also from extinct or dormant comets. The journey from the main belt to near-Earth space is a complex one, driven by a combination of gravitational and non-gravitational forces. The primary mechanism involves the Kirkwood gaps, those resonances with Jupiter we discussed earlier. When main belt asteroids drift into these resonances, usually through the Yarkovsky effect, their orbits become increasingly eccentric. Eventually, they may begin crossing the orbit of Mars, where close encounters with the red planet can further alter their paths, potentially sending them into the inner solar system. The Yarkovsky effect, though tiny, is crucial for delivering asteroids from the main belt. As an asteroid rotates, its afternoon side is warmer than its morning side. When the warm afternoon side rotates into darkness, it continues to radiate heat, creating a tiny thrust. For a typical 1-kilometre asteroid, this force is only about the weight of a coin, but over millions of years, it can change the asteroid's orbit significantly. The direction of drift depends on the asteroid's rotation. Prograde rotators spiral outward, while retrograde rotators spiral inward. Another important delivery mechanism is the new 6 secular resonance, located at the inner edge of the main belt. This resonance involves the precession of an asteroid's orbit synchronizing with Saturn's orbital precession. Asteroids that enter this resonance have their eccentricities pumped up dramatically, often becoming Mars crossers or even Earth crossers within a few million years. Once in near-Earth space, asteroids face a chaotic and ultimately doomed existence. Close encounters with the terrestrial planets constantly alter their orbits in unpredictable ways. Computer simulations show that the typical dynamical lifetime of a near-Earth asteroid is only about 10 million years, before it either collides with a planet, falls into the Sun, or gets ejected from the solar system entirely. This means the NEA population we see today is not the same one that existed when dinosaurs roamed Earth. It's constantly being depleted and replenished. The discovery of near-Earth asteroids has a fascinating history that reflects the evolution of astronomical technology and growing awareness of impact hazards. The first NEA discovered was 433 Eros, found in 1898 by Gustav Witt in Berlin and Auguste Charlois in Nice on the same night. Eros caused immediate excitement because its orbit brought it within 22 million kilometres of Earth, making it an ideal target for measuring solar system distances through parallax. For decades, NEA discoveries were rare and accidental. By 1950, only about a dozen were known. The situation began to change with the advent of dedicated survey programs. The Palomar Planet Crossing Asteroid Survey, begun by Eleanor Helen and Eugene Shoemaker in 1973, was among the first systematic efforts to find NEAs. Using the 48-inch Schmidt telescope at Palomar Observatory, they discovered dozens of new NEAs and began to reveal the true extent of the population. The real revolution came with the development of CCD cameras and automated detection software in the 1990s. The Spacewatch program at Kitt Peak, Arizona, pioneered the use of CCDs for asteroid detection in 1989. Instead of photographic plates that needed to be developed and examined by hand, CCDs provided digital images that could be analysed by computers, dramatically increasing the efficiency of searches. Today, several major surveys scan the skies for NEAs every clear night. The Catalina Sky Survey, operating from Mount Lemmon in Arizona, is currently the most prolific discoverer of NEAs, finding hundreds each year. Pan-STARRS, a panoramic survey telescope and rapid response system, in Hawaii uses a 1.8-meter telescope with a 3 billion pixel camera to survey large areas of sky. ATLAS, Asteroid Terrestrial Impact Last Alert System, operates multiple telescopes designed to find asteroids on their final approach to Earth, providing days to weeks of warning for small impactors. The discovery process is fascinating in its combination of high technology and careful analysis. Modern surveys take multiple images of the same sky region over the course of an hour or two. Software then compares these images, looking for points of light that move against the background stars. When a moving object is detected, its motion is analysed to determine if it matches the expected behaviour of an asteroid. If it's a new discovery, follow-up observations are crucial to determine its orbit accurately. The challenge of finding NEAs is compounded by observational biases. We're most likely to discover asteroids when they're close to Earth and therefore bright, but this is also when their apparent motion across the sky is fastest, making them streak across long exposure images. Asteroids are easier to spot when they're opposite the Sun in the sky, at opposition, but Earth-approaching asteroids spend much of their time in the daylight sky, invisible to ground-based telescopes. Some NEAs are particularly challenging to find. Atira asteroids, with orbits entirely inside Earth's, are only visible during twilight and are often lost in the sun's glare. Small asteroids, those less than about 140 meters in diameter, are usually only detected when they pass very close to Earth. The 20-meter asteroid that exploded over Chelyabinsk, Russia, in February 2013 approached from the daylight side and was completely undetected before impact. As of late 2025, over 35,000 near-Earth asteroids have been discovered, with new ones being found at a rate of about 3,000 per year. Of these, about 2,200 are classified as potentially hazardous asteroids, PHAs, objects larger than 140 meters that can approach Earth within 7.5 million kilometers. While this might sound alarming, it's important to understand that potentially hazardous doesn't mean likely to hit Earth. It's a classification based on orbital parameters that helps prioritize objects for further study. The size distribution of NEAs follows a power law. There are many more small asteroids than large ones. For every kilometer-sized NEA, there are roughly 1,000 100-meter NEAs and 1,000,000 10-meter NEAs. Estimating the total population is challenging because we've only discovered a fraction of what's out there. Current estimates suggest there are about 1,000 NEAs larger than 1 kilometre, of which we've found over 90%. About 25,000 larger than 140 metres, of which we've found about 40%, and millions larger than 10 metres, of which we've found less than 1%. Characterising NEAs goes beyond simply finding them and determining their orbits. Understanding their physical properties, size, shape, composition, rotation rate, and internal structure is crucial for both scientific understanding and planetary defence planning. Various techniques are employed to study NEAs, each providing different pieces of the puzzle. Radar astronomy is one of the most powerful tools for studying NEAs. When an asteroid passes within about 30 million kilometers of Earth, powerful radar transmitters at Goldstone, California, or Arecibo, Puerto Rico, before its collapse in 2020, can bounce radio waves off the asteroid. The return signal provides incredibly detailed information about the asteroid's size, shape, rotation, and surface properties. Radar can achieve resolutions of a few meters for close-passing asteroids, revealing features like craters, boulders, and ridges. Some radar observations have revealed remarkable things. Asteroid 66391 Moshop was found to be a binary system, with a small moon orbiting the primary body. Asteroid 101955. Bennu, target of the OSIRIS-REx sample return mission, was revealed to have a spinning top shape with a pronounced equatorial ridge. Asteroid 99942, Apophis, which will pass within 32,000 kilometers of Earth in 2029, has been extensively studied by radar to refine its orbit and understand its properties. Infrared observations, particularly from space-based telescopes like NOAA's Near-Earth Object Wide Field Infrared Survey Explorer, provide crucial information about asteroid sizes and albedos. Asteroids emit thermal radiation based on their temperature, which depends on their size and how much sunlight they absorb. By observing asteroids at infrared wavelengths, astronomers can determine their diameters much more accurately than from visible light alone. Spectroscopy, analyzing the colors and absorption features in asteroid-reflected sunlight, reveals compositional information. Different minerals absorb and reflect specific wavelengths of light, creating spectral signatures that can be matched to laboratory measurements of meteorites. This allows us to classify NEAs into the same taxonomic types as main belt asteroids and understand what they're made of without visiting them directly. Photometry, measuring how an asteroid's brightness changes over time, reveals rotation periods and can provide information about shape. As an irregular asteroid rotates, it presents different cross-sections to Earth, causing its brightness to vary. The pattern of these variations, called a light curve, can be analysed to determine the rotation period and constrain possible shapes. Some NEAs have been visited by spacecraft, providing ground truth for our remote observations. Near Shoemaker orbited 433 Eros for a year, mapping its surface in detail and eventually landing on it. The Japanese Hayabusa mission visited 25143 Itokawa, returning samples that confirmed it's an S-type asteroid made of ordinary chondrite material. Hayabusa 2 visited 162173 Ryugu, while OSIRIS-REx visited 101955 Bennu, both returning samples of these primitive C-type asteroids. These missions have revealed that NEAs are incredibly diverse worlds, despite their small size. Eros is a consolidated body with a complex geology of craters, grooves, and layered terrains. Itokawa is a rubble pile that looks like two lobes stuck together, covered with boulders and fine regolith. Ryugu and Bennu are also rubble piles, but with very different characteristics. Ryugu is remarkably uniform in colour and composition, while Bennu shows evidence of hydrated minerals and organic compounds. The internal structure of NEAs is particularly important for planetary defence. Many NEAs appear to be rubble piles, collections of rocks held together by gravity rather than material strength. This affects how they would respond to deflection attempts. A rubble pile might absorb the energy of an impact or explosion differently than a solid rock, potentially making some deflection techniques less effective. The rotation rates of NEAs provide clues about their internal structure. No asteroid larger than about 200 meters has been found rotating faster than once every 2.2 hours, the approximate spin rate at which a rubble pile would fly apart from centrifugal force. This spin barrier suggests that most NEAs larger than a few hundred meters are indeed rubble piles. Smaller asteroids can be solid rocks, and some rotate much faster. Asteroid 2028 NM spins once every 42 seconds. Binary NEAs, systems where a small moon orbits a larger primary, make up about 15% of the NEA population. These systems likely form when an asteroid's rotation rate increases through the Yorp effect until material is thrown off from the equator, eventually coalescing into a satellite. Studying binary systems provides information about asteroid densities and internal structure that would be difficult to obtain otherwise. Some NEAs exhibit comet-like activity, blurring the line between asteroids and comets. 3200 Phaethon, the parent body of the Geminid meteor shower, develops a dust tail when near the Sun, despite showing no signs of ice. This activity might be caused by thermal fracturing or desiccation of hydrated minerals. Other active asteroids like P2013 P5 have been observed spinning so fast they're throwing off dust, creating multiple tails that change over weeks. The orbits of NEAs can be incredibly complex and chaotic. Some, like 2002MN, have orbits that are co-orbital with Earth, following horseshoe-shaped paths relative to our planet. Others, like 3753 Cruithne, follow complex quasi-orbital paths that have led to them being incorrectly called Earth's second moon. The asteroid 2016H03 is currently in a quasi-satellite orbit around Earth, circling our planet while orbiting the Sun, and will remain in this configuration for several hundred years. Asteroid families and collisions. The asteroid belt might appear peaceful when viewed from Earth, but it's actually a cosmic shooting gallery where collisions have been shaping and reshaping asteroids for billions of years. These impacts, ranging from gentle bumps that barely disturb surface dust to catastrophic collisions that shatter entire worlds, have created one of the most fascinating features of the asteroid belt: asteroid families. These groups of asteroids, sharing similar orbits and often similar compositions, are the forensic evidence of ancient cosmic crack-ups, and studying them provides unique insights into the collisional evolution of our solar system. Imagine, if you will, two asteroids approaching each other in the darkness of space. They've been orbiting the Sun for billions of years, following paths that have brought them close to each other many times before. But orbital dynamics are complex and chaotic. Tiny gravitational perturbations from Jupiter, thermal forces from uneven heating, close encounters with other asteroids. All these factors slowly change their orbits. This time, their paths intersect exactly. The collision happens in absolute silence. There's no air in space to carry sound waves. But the violence of the impact is extreme. Even at relatively modest closing speeds of a few kilometers per second, the kinetic energy involved is enormous. The impact generates pressures of millions of atmospheres and temperatures of thousands of degrees. Shock waves race through both bodies faster than sound waves travel through rock. In a fraction of a second, solid rock behaves like a fluid, flowing and spraying away from the impact site. What happens next depends on many factors: the sizes of the colliding bodies, their compositions and internal structures, the impact velocity, and the angle of collision. In a catastrophic collision, where a small but fast-moving impactor hits a much larger target, the impact energy can exceed the gravitational binding energy of the target. The asteroid doesn't just crack or crater, it completely shatters, breaking into thousands or millions of fragments that drift apart in an expanding cloud. But here's where gravity performs its delicate dance. While the fragments are separating, they're all still orbiting the Sun. Each fragment inherits slightly different orbital elements based on the velocity it received from the collision. Those ejected in the direction of the parent body's orbital motion end up in slightly higher, slower orbits. Those ejected backward enter lower, faster orbits. Fragments ejected perpendicular to the orbital plane acquire inclination changes. Over time, these fragments spread out along the original orbit, but they remain grouped in orbital element space. They have similar semi-major axes, eccentricities and inclinations. This is an asteroid family, and the process of their formation and evolution tells us remarkable stories about the history of our solar system. The first person to recognize asteroid families was Japanese astronomer Kiyotsugu Hirayama in 1918. By carefully analyzing the orbits of known asteroids, he noticed that certain groups clustered together when plotted in what we now call proper element space, orbital parameters that remain relatively constant over millions of years despite planetary perturbations. Hirayama identified three major groups, which he called families: Coronis, Eos, and Themis. Today, we recognize over 100 asteroid families, each the product of a collision that occurred sometime in the past 4.5 billion years. Identifying asteroid families requires sophisticated analysis. Raw orbital elements change over time due to planetary perturbations, so astronomers calculate proper elements, quasi-constants, that filter out these periodic variations. When asteroids are plotted using proper elements, families appear as concentrations against the background of the general asteroid population. Modern techniques use hierarchical clustering algorithms and statistical methods to identify family members objectively. The age of an asteroid family can be estimated through several methods. One approach uses the fact that family members slowly drift apart due to the Yarkovsky effect. Smaller asteroids drift faster than larger ones because the Yarkovsky force is proportional to surface area, while resistance to orbital change is proportional to mass. By measuring the current spread of family members as a function of size, astronomers can work backward to determine when they were all in the same place, the time of the collision. Another dating method uses the fact that space weathering gradually alters asteroid surfaces, making them redder and darker over time. Fresh surfaces exposed by a collision are greyer and brighter. By comparing the colours of family members to the background population, astronomers can estimate how long ago the collision occurred. Some families also contain asteroids with fresh, unweathered surfaces. These might be fragments from the deep interior of the parent body, exposed for the first time in the collision. Let's explore some of the most interesting and well-studied asteroid families, each telling its own story of cosmic destruction and creation. The Charon family is one of the youngest known families, formed only about 5.8 million years ago, yesterday, in astronomical terms. This youth makes it particularly valuable for study because its members haven't had time to spread far from their initial orbits. The family consists of about 90 members, formed when a roughly 30-kilometre asteroid was catastrophically disrupted. The youth of the Charon family means we can see features that get erased in older families. The original velocity field from the collision is still partially preserved in the orbital distribution of family members. The Veritas family formed about 8.3 million years ago and has been linked to a dramatic event in Earth's history. The collision that created this family produced an enormous amount of dust, some of which spiraled into the inner solar system. Studies of ocean sediments show a spike in extraterrestrial helium-3 about 8.2 million years ago, likely from Veritas family dust. This dust may have contributed to climate changes during the late Miocene epoch. The Baptistina family, formed about 80 million years ago, was once thought to be the source of the asteroid that killed the dinosaurs 66 million years ago. The timing seemed right. Debris from the collision would have had time to drift into Earth-crossing orbits. However, observations by the WISE infrared telescope showed that Baptistina family asteroids are composed of different material than the Chicxulub impactor, ruling out this connection. The search for the dinosaur killers family continues. The Themis family, one of the largest and oldest families at about 2.5 billion years old, has revealed surprising diversity among its members. While most Thermis family asteroids are C-type, as expected from a homogeneous parent body, some members show evidence of water ice on their surfaces. Asteroid 24, Themis itself, has a surface coating of water ice, detected through infrared spectroscopy. Even more remarkably, some Themis family members are main belt comets that occasionally develop comet-like tails, suggesting they contain subsurface ice that occasionally sublimates. The Eos family, formed about 1.3 billion years ago, is one of the largest families, with over 4,000 known members. The parent body was at least 100 kilometers in diameter and appears to have been partially differentiated, with some heating and mineral segregation, but not complete melting. This makes Eos family members valuable for understanding thermal processing in medium-sized asteroids. The Flora family is particularly important because it's located near the NU6 secular resonance at the inner edge of the main belt. This location makes it an efficient source of meteorites. Fragments knocked off Flora family members can be delivered to Earth-crossing orbits within a few million years. Many of the ordinary chondrite meteorites in our collections likely originated from Flora family asteroids. The Hygiea family tells a story of extreme destruction. The parent body was probably over 400 kilometers in diameter, yet it was completely shattered by an impact. Remarkably, 10 Hygiea itself, the fourth largest asteroid, appears to be the largest fragment of this collision. Recent observations show that Hygiea is nearly spherical, suggesting it's a reaccumulated body, fragments from the original collision that came back together under their mutual gravity to form a new, round asteroid. Not all families formed from catastrophic disruptions. Some are the results of cratering events where a large impact excavated material from an asteroid without destroying it. The Vesta family is the prime example. A giant impact near Vesta's south pole created the Rhea Silvia basin and ejected about 1% of Vesta's mass into space. These fragments, called Vestoids, have orbits similar to Vesta and matching spectral properties. Some have been delivered to Earth as HED meteorites, giving us samples of Vesta's interior. The study of asteroid families has revealed fundamental insights about impact physics and asteroid interiors. The size distribution of family members, how many large fragments versus small ones, depends on the internal structure of the parent body and the energy of the impact. Monolithic asteroids tend to produce a few large fragments and many small ones following a power law distribution. Rubble piles produce different fragment distributions with more equal-sized pieces. The escape velocity from asteroids plays a crucial role in family formation. For a 100-kilometer asteroid, escape velocity is only about 50 meters per second. Collision fragments need to exceed this speed to escape and become independent asteroids. Slower fragments fall back onto the largest remnant or enter orbit around it, potentially forming moons. This process, called gravitational reaccumulation, can create binary asteroids or reform rubble pile asteroids from collision debris. Some families show evidence of multiple collisions. The Coronis family, formed about 2 billion years ago, contains several subclusters that appear to be secondary families, the result of later collisions among family members. These families within families demonstrate that collisional evolution is an ongoing process, with asteroids being repeatedly broken apart and reformed over solar system history. The colours and spectra of family members provide information about the interior structure of their parent bodies. In a differentiated asteroid with distinct layers, a catastrophic collision would produce fragments with different compositions, metallic pieces from the core, olivine-rich fragments from the mantle, basaltic chunks from the crust. The Gaffey family shows exactly this kind of diversity, suggesting its parent was a differentiated body similar to Vesta. Other families show remarkable uniformity in composition, indicating their parents were homogeneous rubble piles or undifferentiated bodies. The Carin family members all have nearly identical spectra, suggesting they came from a homogeneous parent body, or perhaps all came from a similar depth within a layered parent. The orbital evolution of families is complex and fascinating. Initially, family members are concentrated in orbital element space, but various dynamical effects cause them to spread over time. The Yarkovsky effect causes a size-dependent drift in semi-major axis, with smaller fragments typically experiencing greater mobility and spreading more widely throughout the main belt. This thermal effect, combined with planetary perturbations, gradually erases the initial kinematic properties of smaller family members over millions of years. Think of it like this: immediately after the collision that creates a family, all the fragments are close together in space and have similar orbits. But from that moment on, each fragment begins its own journey. The smallest pieces, perhaps meter-sized boulders, feel the Yarkovsky effect most strongly relative to their mass. As they rotate in sunlight, the afternoon side gets warm, and as this warm face rotates into darkness, it radiates heat in a specific direction, creating a tiny but persistent thrust. Over millions of years, this can change their orbits dramatically. Larger family members, those tens of kilometers across, feel the Yarkovsky effect too, but their greater mass makes them more resistant to orbital changes. This creates what astronomers call a size-dependent spreading of the family. If you plot family members by size and orbital elements, you see a distinctive V-shaped pattern, with smaller asteroids spread farther from the family centre. This pattern is so characteristic that it's now used as one method to determine family ages. The wider the V, the older the family. But the Yarkovsky effect isn't the only force at work. Close encounters with massive asteroids can dramatically alter family members' orbits. Nearly all asteroids in the main belt occasionally pass near one of the big four, Ceres, Vesta, Pallas or Hygeia. While these encounters rarely result in collisions, the gravitational perturbations can pump up eccentricities and inclinations, scattering family members away from their initial grouping. Mean motion resonances with Jupiter act like escape hatches for family members. As asteroids drift due to the Yarkovsky effect, some inevitably encounter these resonances. Once captured, their orbits can change dramatically within just a few million years. A family member that enters the 3-to-1 resonance with Jupiter might find its eccentricity pumped up until it becomes a Mars crosser, then an Earth crosser, and eventually either collides with a planet or gets ejected from the inner solar system entirely. Secondary collisions among family members and with background asteroids continuously modify the family population. These collisions serve multiple roles in family evolution. Large impacts can create subfamilies within the main family, producing secondary clusters in orbital element space. Smaller impacts gradually grind down family members, creating a cascade of ever smaller fragments. The smallest fragments, once they're reduced to sizes of a few meters or less, can be removed from the asteroid belt entirely by radiation pressure from sunlight. The interplay between all these effects creates complex evolutionary patterns. Young families, those less than 10 million years old, often still show the initial velocity field from their formation. The fastest moving fragments from the original collision are found at the edges of the family in orbital space, while slower fragments cluster near the centre. But as families age, this initial structure gets overprinted by subsequent evolution. The Yarkovsky drift dominates for intermediate-sized members. Resonances capture and remove asteroids at certain orbital distances, and collisions continuously modify the size distribution. Some families show evidence of interesting evolutionary phenomena. The Coronis family, for example, has several distinct subclusters that appear to be secondary families created by collisions among family members long after the original family-forming event. These families within families have their own age estimates and evolutionary histories, creating a complex nested structure in orbital element space. The Eos family demonstrates how composition can affect family evolution. Some Eos members have albedos significantly different from the majority, suggesting they might be interlopers, background asteroids that happen to have similar orbits but aren't genetic family members. Distinguishing true family members from interlopers requires combining orbital analysis with spectroscopic observations to ensure compositional similarity. The evolution of the Vesta family is particularly interesting because we can still see the parent body. The Vestoids, fragments blasted off Vesta by the impacts that created the Rhea Silvia and Venonia basins, form a bridge in orbital element space between Vesta and the 3-to-1 resonance with Jupiter. This resonance acts as an escape route, delivering Vesta fragments to Earth-crossing orbits, where they eventually fall to Earth as head meteorites. We can literally trace the path from a specific crater on Vesta to meteorites in our museums. Missions to asteroids, touching ancient worlds. The story of humanity's direct exploration of asteroids is one of audacious engineering, patient planning, and remarkable discoveries that have transformed our understanding of these ancient worlds. Each mission to an asteroid represents years or decades of preparation, innovative solutions to unprecedented challenges, and the collective dreams of thousands of scientists and engineers. These robotic explorers have revealed asteroids to be far more diverse and complex than we ever imagined, each one a unique world with its own history, written in craters, boulders, and dust. The journey to explore asteroids directly began not with a dedicated asteroid mission, but with a spacecraft designed for another purpose entirely. In October 1991, NASA's Galileo spacecraft, on its way to Jupiter, flew past asteroid 951 Gaspra at a distance of 1,600 kilometers. This encounter, lasting just minutes, provided our first close-up images of an asteroid. Gaspra appeared as an irregular, potato-shaped body about 18 kilometers long, its surface peppered with craters but surprisingly lacking in large ones, suggesting a relatively young surface age of only a few 100 million years. 2 years later, in August 1993, Galileo encountered a second asteroid, 243 Ida, and made an astonishing discovery. Ida had a moon. The tiny satellite, named Dactyl, was only 1.4 kilometers across, orbiting about 100 kilometers from Ida. This was the first confirmed asteroid moon, proving that asteroids could have their own satellites, and opening up new ways to determine asteroid masses and densities through orbital dynamics. These flyby encounters, brief as they were, whetted scientists' appetites for more detailed exploration. What was needed was a mission that could rendezvous with an asteroid, orbit it, and study it in detail over an extended period. That mission was NEAR, the Near-Earth Asteroid Rendezvous spacecraft, later renamed NEAR Shoemaker, in honor of planetary geologist Eugene Shoemaker. NEAR Shoemaker launched in February 1996 with a primary target of 433 Eros, one of the largest near-Earth asteroids. The journey to Eros wasn't direct. Orbital mechanics required a circuitous path, including an Earth gravity assist. Along the way, NEAR flew past main belt asteroid 253 Matilda in June 1997, revealing it to be a primitive C-type asteroid with a surprisingly low density, suggesting a rubble pile structure with significant void space. On February 14, 2000, Valentine's Day, appropriately, for an asteroid named after the Greek god of love, near Shoemaker successfully entered orbit around Eros. This was a historic moment, the first time a spacecraft had orbited an asteroid. For the next year, NEAR mapped Eros in exquisite detail, gradually spiralling closer to the surface. Eros revealed itself to be a fascinating world. 34 kilometers long and shaped somewhat like a peanut, its surface told a complex geological story. There were craters of all sizes, from giant depressions like Psyche crater to tiny pits just meters across. Strange grooves ran across the surface, possibly fractures from ancient impacts. Most mysteriously, Eros had ponds, smooth flat areas in crater floors that looked almost like dried lake beds, though they were likely formed by seismic shaking that caused fine material to settle into level surfaces. The mission's finale was never part of the original plan, but became one of its most dramatic achievements. After completing its mapping mission controllers decided to attempt landing near on Eros' surface. On February 12, 2001, NEAR Shoemaker touched down successfully, becoming the first spacecraft to land on an asteroid. Even more remarkably, the spacecraft survived the landing and continued transmitting data for 2 more weeks, including gamma-ray spectrometer measurements that provided information about surface composition. While NEAR Shoemaker was exploring Eros, the Japanese space agency, JAXA, was preparing its own ambitious asteroid mission. Hayabusa, meaning falcon in Japanese, launched in May 2003 with an audacious goal: not just to visit an asteroid, but to collect samples and return them to Earth. Hayabusa's target was 25143 Itokawa, a small near-Earth asteroid only about 350 meters long. The journey to Itokawa was plagued with difficulties. Solar flares damaged the solar panels, reducing available power. Reaction wheels used for attitude control failed one by one. Yet through ingenious engineering solutions, including using the ion engine's slight thrust for attitude control, the spacecraft reached Itokawa in September 2005. What Hayabusa found at Itokawa challenged our understanding of small asteroids. Instead of a solid rock, Itokawa appeared to be a rubble pile, a collection of boulders and rocks held together by weak gravity. Its shape resembled 2 lobes stuck together, possibly the result of 2 separate bodies gently merging. The surface was unlike anything seen before, with areas of rough boulders adjacent to smooth seas of fine gravel. There were no visible impact craters, suggesting that seismic shaking from impacts caused the surface to reorganize rather than forming permanent craters. The sample collection attempts were fraught with problems. The sampling mechanism, designed to fire a projectile into the surface and collect the ejected material, malfunctioned. During 2 touchdown attempts in November 2005, it was unclear whether any samples had been collected. The spacecraft then suffered a fuel leak and lost communication with Earth for several weeks. When contact was finally restored, Hayabusa was tumbling and had lost much of its fuel. The journey home became an epic tale of perseverance. With failed reaction wheels, limited fuel, and degraded ion engines, the trip that should have taken 3 years stretched to 7. Engineers had to combine partially functioning ion engines in ways never originally intended, essentially rebuilding the propulsion system in flight. Finally, on June 13, 2010, Hayabusa's sample return capsule streaked across the Australian sky and landed in the Woomera Desert. When scientists opened the capsule, they found it contained about 1,500 tiny grains, less than a milligram of material, but enough to revolutionize our understanding of asteroids. These grains confirmed that S-type asteroids like Itokawa are the source of ordinary chondrite meteorites, the most common type of meteorite on Earth. They also revealed details about space weathering, how exposure to solar wind and cosmic rays alters asteroid surfaces over time. The success of Hayabusa, despite all its challenges, inspired more ambitious sample return missions. Hayabusa 2 launched in the December 2014, targeting 162173 Ryugu, a C-type asteroid about 900 meters in diameter. Learning from the first mission's difficulties, Hayabusa 2 carried improved systems and backup equipment. Arriving at Ryugu in June 2018, Hayabusa 2 found a world very different from Itokawa. Ryugu was remarkably dark, reflecting only about 2% of sunlight, and shaped like a spinning top with a pronounced equatorial ridge. Its surface was strewn with boulders, many containing bright inclusions that might be altered minerals from ancient water interactions. The spacecraft deployed several small landers and rovers, including Mascot, Mobile Asteroid Surface Scout, provided by the German and French space agencies, which hopped across the surface, taking measurements. Hayabusa 2 successfully collected samples from 2 different locations on Ryugu. In a spectacular operation, it even created an artificial crater using a copper impactor, then collected samples from beneath the surface, material that had been shielded from space weathering for possibly billions of years. The spacecraft departed Ryugu in November 2019 and delivered its precious cargo to Earth on December 5, 2020. The Ryugu samples, totaling about 5.4 grams, have provided extraordinary insights. They contain organic molecules, including amino acids, and show evidence of aqueous alteration, chemical changes caused by liquid water. The samples are extremely primitive, resembling the most primitive carbonaceous chondrite meteorites, but even more fragile and porous. Some grains would never survive atmospheric entry as meteorites, meaning these samples give us access to solar system material we could never study otherwise. Meanwhile, NASA's OSIRIS-REx, Origins, Spectral Interpretation, Resource Identification, and Security Regolith Explorer mission was conducting its own sample return mission to asteroid 101955 Bennu. Launched in September 2016, OSIRIS-REx arrived at Bennu in December 2018. Bennu, another C-type asteroid about 500 meters in diameter, proved to be full of surprises. Like Ryugu, it had a spinning top shape with an equatorial ridge, but its surface was even more challenging for sample collection, covered with boulders and with very few smooth areas. Most surprisingly, Bennu was observed ejecting particles from its surface, making it an active asteroid. These ejection events, possibly caused by thermal fracturing or volatile release, created a tenuous cloud of particles around the asteroid. The sample collection by OSIRIS-REx in October 2020 was dramatically successful, perhaps too successful. The TAG-SAM, touch-and-go sample acquisition mechanism, collected so much material that larger rocks wedged the collection chamber open, causing some sample to leak out. Quick action by the mission team secured the sample, and the spacecraft departed Bennu in May 2021. OSIRIS-REx delivered its samples to Earth on September 24, 2023, with the capsule landing in the Utah desert. The returned samples, totaling about 250 grams, are the largest asteroid sample ever returned to Earth. Initial analysis shows the material is rich in carbon and water-bearing minerals, with carbon comprising up to 5% by weight in some samples. The samples also contain sulfide minerals that would be destroyed if they fell to Earth as meteorites, preserving evidence of chemical processes from the early solar system. While these sample return missions captured the spotlight, other missions were exploring asteroids in different ways. NASA's Dawn mission, launched in September 2007, used ion propulsion to visit and orbit 2 of the largest asteroids, Vesta, and Ceres. Dawn arrived at Vesta in July 2011, becoming the first spacecraft to orbit a main belt asteroid. Over the next year, it mapped Vesta in detail, revealing a differentiated world with an iron core, rocky mantle, and basaltic crust, more like a planet than a typical asteroid. The giant impact basins Rhea Silvia and Venonaya at Vesta's south pole told of ancient collisions that nearly shattered this protoplanet. Dark material on Vesta's surface, likely delivered by carbon-rich impactors, created a complex pattern of albedo variations. In March 2015, Dawn arrived at Ceres, becoming the first spacecraft to orbit a dwarf planet. Ceres proved to be a world of ice and rock, possibly harbouring a subsurface ocean. The bright spots that had puzzled astronomers turned out to be deposits of sodium carbonate and other salts, likely deposited by briny water erupting from below. Ahuna Mons, a 4-kilometre-high mountain, appeared to be a young cryovolcano. Organic molecules were detected on the surface, adding to Ceres's astrobiological interest. The European Space Agency's Rosetta mission, while primarily focused on Comet 67 P. Churyumov-Gerasimenko, also visited 2 asteroids during its journey. In September 2008, it flew past 2867 Steins, a small E-type asteroid that appeared diamond-shaped due to a large crater that removed much of its southern hemisphere. In July 2010, Rosetta encountered 21 Lutetia, a large M-type asteroid about 100 kilometres across, revealing a battered world with a complex geology, including grooves, scarps, and regions of different ages. China entered asteroid exploration with the Chang'e 2 lunar probe, which after completing its moon mission, flew past asteroid 4179 Tutatis in December 2012. The flyby revealed Tutati to be a contact binary, 2 bodies joined together, with a complex rotation state that causes it to tumble rather than spin around a single axis. Looking to the future, several exciting asteroid missions are underway or in development. NASA's Psyche mission, launched in October 2023, is en route to asteroid 16 Psyche, a large M-type asteroid that may be the exposed iron core of a protoplanet. Arrival is expected in August 2029. Studying Psyche could give us insights into planetary cores that we could never obtain otherwise, as we cannot directly access Earth's core. NASA's Lucy mission, launched in October 2021, is on an ambitious 12-year journey to visit 8 asteroids, including 7 Jupiter Trojans. These asteroids, locked in Jupiter's Lagrange points, are thought to be pristine remnants from the outer solar system, possibly captured during planetary migration. Lucy will provide our first close-up look at these mysterious objects. The European Space Agency's Hera mission, launching in October 2024, will visit the binary asteroid system Didymos and Dimorphos. This system was the target of NASA's DART, Double Asteroid Redirection Test, mission, which intentionally crashed into Dimorphos in September 2022 to test planetary defense techniques. Hera will study the aftermath of this impact, providing crucial data about how to deflect potentially hazardous asteroids. JAXA is developing the Destiny Plus mission to fly past asteroid 3200 Phaethon, the parent body of the Geminid meteor shower. This unusual asteroid shows comet-like activity despite no evidence of ice, possibly due to thermal fracturing or desiccation of hydrated minerals. Understanding Phaethon could help explain the continuum between asteroids and comets. Each mission to an asteroid requires overcoming unique challenges. The weak gravity of asteroids, typically less than 1/10,000th of Earth's gravity, makes orbital operations completely different from orbiting planets. Spacecraft must move slowly and carefully, as a small thruster firing could easily exceed escape velocity. Landing on an asteroid is more like docking with another spacecraft than landing on a planet. Communication delays present another challenge. When exploring distant asteroids, radio signals can take tens of minutes to travel between Earth and the spacecraft. This means spacecraft must be highly autonomous, capable of making decisions without real-time human input. During critical operations like sample collection, the spacecraft must execute complex sequences entirely on their own. The irregular shapes and weak gravity of asteroids create chaotic gravitational fields. Instead of nice, elliptical orbits, spacecraft trajectories around asteroids can be complex three-dimensional curves. Mission planners must carefully model these fields and design stable orbits that won't inadvertently crash into the asteroid or escape to space. Power generation is always a concern for deep space missions. Solar panels must be large enough to generate sufficient power at asteroid distances from the Sun, yet light enough to be practical. Some missions, like Dawn, use ion propulsion, which is highly efficient but requires substantial electrical power. Others use conventional chemical propulsion, but must carefully manage limited fuel supplies. The scientific instruments on asteroid missions are marvels of miniaturization and efficiency. Cameras must work in extreme lighting conditions, from brilliant sunlight to pitch-black shadows. Spectrometers must identify minerals from reflected light across multiple wavelengths. Laser altimeters map surface topography by timing laser pulses. Magnetometers search for evidence of ancient magnetic fields. Each instrument must be lightweight, reliable, and able to operate in the harsh environment of space. Sample return missions face additional challenges. The samples must be collected without contamination, stored safely for years in space, protected during the fiery re-entry to Earth's atmosphere, and recovered quickly after landing. The sample return capsules are engineering masterpieces, using ablative heat shields to survive re-entry and parachutes to land gently. Asteroids and life on Earth. The relationship between asteroids and life on Earth is one of creation and destruction, of bringing the ingredients for life and occasionally ending it in catastrophic impacts. This cosmic duality has shaped the history of our planet and every living thing that has ever existed upon it. From delivering water and organic molecules to the young Earth, to triggering mass extinctions that redirected the course of evolution, asteroids have been silent partners in the story of life for billions of years. To understand this relationship, we must journey back to Earth's earliest days, over 4.5 billion years ago. The young Earth was a hellish place, nothing like the blue marble we know today. The planet had just formed from the accretion of countless planetesimals in the inner solar system, and its surface was likely an ocean of molten rock, constantly bombarded by leftover debris from planetary formation. This period, aptly named the Hadean Aeon after the Greek god of the underworld, lasted from Earth's formation until about 4 billion years ago. During the Hadean, Earth was subjected to what scientists call the late heavy bombardment, though there's ongoing debate about whether this was a distinct spike in impact rates or simply the tail end of planetary accretion. Regardless, the young Earth was pummeled by asteroids and comets at a rate thousands of times higher than today. The Moon's heavily cratered highlands preserve a record of this bombardment. Every large circular feature you can see on the Moon with binoculars represents an ancient impact, and Earth, with its larger size and stronger gravity, would have attracted even more impactors. These early impacts were so frequent and so violent that they repeatedly sterilized Earth's surface. Any early attempts at life would have been extinguished as massive impacts vaporized oceans and turned the surface into molten rock. Yet paradoxically, these same impacts may have been crucial for making Earth habitable. Asteroids and comets delivered volatile compounds: water, carbon dioxide, methane, ammonia, that formed Earth's early atmosphere and oceans. While Earth formed with some water, much of our planet's surface water may have been delivered by carbonaceous asteroids and comets during this bombardment period. Even more intriguingly, carbonaceous asteroids delivered complex organic molecules, the building blocks of life. We know from studying carbonaceous chondrite meteorites that these asteroids contain amino acids, nuclear bases, sugars, and other organic compounds that form the basis of biochemistry. The Murchison meteorite alone contains over 70 different amino acids. These molecules, formed in the cold depths of space or in the warm, wet interiors of asteroid parent bodies, rained down on the early Earth, creating a rich organic soup from which life could emerge. As the bombardment rate declined around 3.9 billion years ago, Earth's surface finally stabilized enough for life to take hold. The earliest evidence for life on Earth dates to about 3.5 billion years ago. Stromatolites and microfossils preserved in ancient rocks. But life's hold on the planet remained tenuous, subject to the continued, if less frequent, arrival of cosmic projectiles. Throughout Earth's history, asteroid impacts have punctuated the evolutionary story with periods of devastation and renewal. The geological record preserves evidence of these impacts in the form of impact craters, though Earth's active geology, plate tectonics, erosion, sedimentation, has erased most ancient craters. Only about 200 impact structures have been identified on Earth, compared to hundreds of thousands on the Moon. Yet these represent only the most recent and largest impacts. One of the best preserved impact structures is Meteor Crater in Arizona, formed about 50,000 years ago when an iron asteroid roughly 50 meters in diameter struck the desert at about 12 kilometers per second. The explosion, equivalent to about 10 megatons of TNT, excavated a crater 1.2 kilometers across and 170 meters deep. The asteroid itself was almost entirely vaporized, though fragments of meteoric iron are still found scattered around the crater. Meteor Crater is small compared to some impact structures. The Chicxulub crater in Mexico's Yucatan Peninsula, buried under hundreds of meters of sediment, is about 180 kilometers in diameter. The Vredefort structure in South Africa, heavily eroded but still visible, was originally perhaps 300 kilometers across. The Sudbury Basin in Canada, now filled with valuable nickel and copper ores, concentrated by the impact, represents a 2 billion-year-old impact structure, originally about 250 kilometers in diameter. But it's the Chicxulub impact, occurring 66 million years ago at the end of the Cretaceous period, that most captures our imagination. This event, caused by an asteroid or comet roughly 10 kilometers in diameter, ended the age of dinosaurs and ushered in the age of mammals, ultimately leading to our own existence. The story of discovering the cause of the dinosaurs' extinction is itself fascinating. In 1980, Luis and Walter Alvarez, along with colleagues, discovered a thin layer of clay at the Cretaceous-Paleogene boundary that was enriched in iridium, an element rare on Earth's surface but common in asteroids. This iridium layer, found at sites around the world, suggested a massive asteroid impact had spread debris globally. The discovery was initially controversial. Many scientists favoured volcanic eruptions or gradual climate change as extinction causes. The smoking gun was found in 1990 when researchers identified the Chicxulub crater buried beneath the Yucatan Peninsula. The crater's age matched the extinction event perfectly. Further evidence accumulated, shocked quartz grains that could only form under extreme pressure, spherules of impact glass, and tsunami deposits around the ancient Gulf of Mexico. The Chicxulub impact released energy equivalent to billions of nuclear weapons. The immediate effects were catastrophic within thousands of kilometers. A fireball that incinerated everything within line of sight, hurricane-force winds, and earthquakes exceeding magnitude 10. Massive tsunamis, perhaps a kilometer high, swept across the Gulf of Mexico and Atlantic Ocean. But the global effects were even more devastating. The impact threw enormous amounts of debris into the atmosphere. The finest particles remained suspended for months or years, blocking sunlight and causing impact winter. Photosynthesis shut down, temperatures plummeted, and food chains collapsed. Sulfur-rich rocks at the impact site vaporized, creating sulfuric acid aerosols that caused acid rain. Wildfires, possibly ignited by hot debris raining back from space, consumed forests worldwide, adding soot to the atmospheric cocktail. The extinction was selective in telling ways. Animals larger than about 25 kilograms went extinct, unable to find enough food or shelter. Marine ecosystems collapsed as photosynthetic plankton died. Yet some groups survived. Small mammals that could burrow and required less food, birds that were small and could fly to find resources, crocodilians that could go months without eating, and various plants whose seeds could remain dormant until conditions improved. The Chicxulub impact wasn't unique in causing mass extinction. The Permian Triassic extinction, 252 million years ago, the largest mass extinction in Earth's history, may have been triggered or exacerbated by one or more large impacts, though massive volcanism in Siberia was likely the primary cause. The Triassic-Jurassic extinction, 201 million years ago, coincides with the Manicouagan impact structure in Canada, though the connection remains debated. Even smaller impacts can have significant effects on climate and evolution. The Popigai impact in Siberia 35 million years ago coincides with a period of global cooling. The Chesapeake Bay impact 35 million years ago created a crater 90 kilometers wide and may have contributed to climate changes at the Eocene-Oligocene boundary. These impacts, while not causing mass extinctions, may have accelerated evolutionary changes by altering environments and creating new ecological niches. In more recent history, asteroid impacts have continued to influence human civilization, though usually in subtle ways. The Tunguska event of June 30th, 1908 remains the largest impact event in recorded history. An asteroid or comet fragment, probably 30 to 50 meters in diameter, exploded in the atmosphere above Siberia with the force of 10 to 15 megatons of TNT. The explosion flattened 2,000 square kilometers of forest, knocking down 80 million trees. If this had occurred over a populated area, the casualties would have been catastrophic. The Chelyabinsk event of February 15, 2013, provided a modern reminder of the ongoing threats. A 20-meter asteroid entered Earth's atmosphere over Russia, exploding at an altitude of about 30 kilometers with the energy of 500 kilotons of TNT. The shockwave damaged thousands of buildings and injured over 1,500 people, mostly from flying glass as windows shattered. This event was particularly sobering because the asteroid approached from the sun's direction and was completely undetected before impact. These recent events highlight an important point. Asteroid impacts aren't just ancient history. They're an ongoing process that continues today. Every day, Earth is struck by about 100 tons of cosmic material, mostly dust and small particles that burn up harmlessly in the atmosphere as meteors. Larger impacts are less frequent but follow a predictable statistical distribution. Tunguska-sized events occur roughly once per century. Chicxulub-sized impacts occur perhaps once per 100 million years. Understanding this impact frequency is crucial for assessing the risk to human civilization. A 1-kilometre asteroid impact, while not causing a mass extinction, could kill millions directly and billions indirectly through climate effects and agricultural collapse. Such impacts occur roughly once per 500,000 years. A 100-metre asteroid could destroy a city or cause a devastating tsunami if it hit the ocean. These impacts occur perhaps once per 10,000 years. But asteroids haven't only brought destruction to Earth, they've also delivered valuable resources. Iron meteorites were among the first sources of iron used by humans before smelting was developed. The iron in these meteorites, already in metallic form and often alloyed with nickel, was superior to early smelted iron. King Tutankhamun's tomb contained a dagger made from meteoritic iron, and the Inuit of Greenland used iron from the Cape York meteorite for tools for centuries. Some impact structures have concentrated valuable minerals. The Sudbury Basin in Canada, formed by an impact 2 billion years ago, contains one of the world's largest nickel and copper deposits. The impact melted enormous volumes of rock, allowing heavy metals to settle and concentrate. The Vredefort impact in South Africa may have helped concentrate the gold deposits of the Witwatersrand Basin, though this connection is debated. Asteroids continue to deliver scientific treasures in the form of meteorites. These space rocks provide samples of asteroids, Mars, and even the Moon without the expense of space missions. They've revealed the age of the solar system, the conditions in the solar nebula, and the processes that formed planets. Some meteorites contain pre-solar grains, actual stardust older than our solar system, providing information about stellar nucleosynthesis and galactic chemical evolution. The organic molecules in carbonaceous chondrites have profound implications for the origin of life. These meteorites contain amino acids with a slight excess of left-handed forms, the same handedness used by life on Earth. This suggests that the molecular asymmetry fundamental to biochemistry might have been delivered from space. Meteorites also contain nuclear bases, components of DNA and RNA, and sugar-related compounds, providing a cosmic source for life's building blocks. The ongoing delivery of organic molecules by meteorites and interplanetary dust particles may have been crucial for life's origin and early evolution. Laboratory experiments show that impact events can synthesize organic molecules from simpler precursors, suggesting impacts themselves might have contributed to prebiotic chemistry. Impact craters, with their fractured rock and hydrothermal systems, may have provided protected environments where early life could have evolved. The relationship between impacts and evolution extends beyond mass extinctions. Impacts create new environments. Crater lakes, hydrothermal systems, shocked and fractured rock that can become evolutionary laboratories. The Ries crater in Germany, formed 15 million years ago, filled with a lake that persisted for 2 million years, accumulating sediments that preserve a detailed record of post-impact biological recovery and evolution. Impact events may have influenced human evolution specifically. The Australasian tektite-strewn field, created by a large impact about 790,000 years ago, though the crater hasn't been found, coincides with significant changes in human populations and stone tool technology. While correlation doesn't prove causation, the climate effects of this impact may have created evolutionary pressures that influenced human development. Looking to the future, our growing understanding of asteroid impacts has led to the development of planetary defense strategies. We now track potentially hazardous asteroids, those larger than 140 meters that can approach Earth within 7.5 million kilometers. As of late 2025, over 2,000 such objects are known, and none pose a threat in the next century. But the search continues because we've only found an estimated 40% of potentially hazardous asteroids. New surveys, both ground-based and space-based, aim to complete the inventory. The Vera Rubin Observatory, beginning operations soon, will revolutionize asteroid discovery with its ability to survey the entire visible sky every few nights. If we do find an asteroid on a collision course with Earth, we now have potential mitigation strategies. The DART mission's successful deflection of asteroid Dimorphos in September 2022 demonstrated that we can change an asteroid's orbit. For longer warning times, even a tiny change in velocity, perhaps just millimeters per second, could cause an asteroid to miss Earth if applied years or decades before the predicted impact. Other deflection strategies are being studied. Gravity tractors that slowly pull asteroids off course, ion beam deflection that gradually pushes them, or in extreme cases, nuclear deflection for large asteroids with short warning times. The key is early detection. The more warning time we have, the easier deflection becomes. Mining the sky, the future of asteroids. As we stand at the threshold of becoming a spacefaring civilization, asteroids transform from cosmic threats and scientific curiosities into something else entirely. Resources. The same bodies that delivered death to the dinosaurs may deliver prosperity to future generations, providing the raw materials necessary for humanity's expansion beyond Earth. The concept of asteroid mining, once pure science fiction, has evolved into serious business propositions, technological development programs, and policy discussions at the highest levels of government and industry. The appeal of asteroid mining lies in the extraordinary wealth these bodies represent. A single metallic asteroid like 16 Psyche contains enough iron and nickel to supply Earth's needs for millions of years. The platinum group metals in just one modest-sized metallic asteroid could exceed all the platinum ever mined on Earth. But perhaps more importantly for space exploration, asteroids contain vast quantities of water, the most valuable resource in space, useful for drinking, breathing, when split into hydrogen and oxygen, radiation shielding, and rocket fuel. Consider the economics of space resources from a different perspective. Launching anything from Earth's surface to orbit costs thousands of dollars per kilogram, even with the most efficient modern rockets. Every litre of water, every kilogram of fuel, every structural beam used in space must overcome Earth's gravity well at enormous expense. But asteroids are already in space. Their resources can be extracted and used with far less energy than launching equivalent materials from Earth. The water alone in near-Earth asteroids could revolutionize space exploration. A single small C-type asteroid, perhaps 100 meters in diameter, might contain millions of tons of water. This water, converted to rocket fuel through electrolysis powered by solar panels, could refuel spacecraft heading to Mars or the outer planets. Instead of carrying all their fuel from Earth, missions could launch with just enough propellant to reach a nearby asteroid depot, refuel, and continue their journey. This changes the entire economics of space exploration, making missions that are currently impossible suddenly feasible. The technology to extract water from asteroids is already being developed. One promising approach, called optical mining, uses concentrated sunlight focused by mirrors to heat asteroid material and extract water and other volatile compounds. The extracted water vapour would be captured and condensed, then stored as ice or liquid, depending on the application. Solar panels would provide power for electrolysis, splitting water into hydrogen and oxygen for rocket fuel, or the water could be used directly as propellant in simpler resistor-jet engines. The business case for asteroid water is compelling. Launching water from Earth to geostationary orbit costs roughly $20,000 per kilogram with current technology. A satellite that needs 1,000 kilograms of propellant for station keeping over its lifetime represents $20 million just in launch costs for that propellant. But if that same water could be delivered from an asteroid, the economics change dramatically. Even if asteroid-derived water initially costs $5,000 per kilogram, a quarter of Earth launch costs, the savings are enormous. This creates what space economists call the virtuous cycle of space resources. The first asteroid mining operations will likely focus on water for satellite refueling, a market worth billions of dollars annually. The profits from this enable development of more sophisticated extraction equipment, which reduces costs, which opens new markets, which funds further development. Eventually, the infrastructure exists to support large-scale human activities in space without the crushing expense of launching everything from Earth. But water is just the beginning. Carbonaceous asteroids contain carbon compounds that can be processed into plastics and other organic materials. Carbon dioxide and water can be combined to create methane and oxygen, a powerful rocket fuel combination. The carbon itself could be formed into carbon fiber, an incredibly strong and lightweight structural material, perfect for space construction. Imagine building spacecraft, space stations, even colonies from materials sourced entirely in space, without the expense and limitations of Earth launch. Metallic asteroids offer even more tantalizing possibilities. The iron and nickel in these bodies could be used directly for construction. Iron is actually an excellent material for space structures, where weight isn't a concern, but radiation shielding is important. The platinum group metals, while valuable on Earth, are also crucial for many industrial processes. Platinum is an excellent catalyst for fuel cells, which could provide power for spacecraft and space settlements. Iridium and osmium have unique properties useful in electronics and advanced materials. The rare Earth elements found in some asteroids are particularly interesting. These elements, despite their name, they're not actually that rare on Earth, just difficult to extract in concentrated form, are crucial for modern technology. Neodymium for powerful magnets, europium for display screens, yttrium for lasers and superconductors. As Earth's easily accessible deposits are depleted and environmental concerns limit mining, space-based sources become increasingly attractive. Consider asteroid 16 Psyche, currently being visited by NASA's Psyche mission. This 220-kilometre metallic asteroid contains enough iron to supply Earth's needs for millions of years. The nickel content alone is worth approximately $10,000 quadrillion at current prices. Though obviously, returning that much nickel to Earth would crash the market. The real value isn't in bringing these metals to Earth, but in using them in space, where their value is multiplied by the cost of launch from Earth. The technical challenges of asteroid mining are substantial, but not insurmountable. The first challenge is simply getting to the asteroid. While near-Earth asteroids are more accessible than the Moon in terms of delta V, change in velocity required, journey times can be long, months or years depending on the target and the type of propulsion used. Ion drives, which are highly efficient but produce low thrust, are ideal for cargo missions where time isn't critical. Chemical rockets could deliver mining equipment faster, but at higher cost. Once at the asteroid, the next challenge is anchoring to it. Most asteroids have such weak gravity that traditional landing isn't possible. You don't land on an asteroid so much as dock with it. The European Space Agency's Rosetta mission demonstrated the difficulty when its Philae lander bounced several times on Comet 67 P. Churyumov-Gerasimenko before coming to rest in an unfortunate shadow. Mining equipment will need to anchor itself securely, perhaps using harpoons, drills, or nets that wrap around smaller asteroids. The actual extraction process depends on the asteroid type and the desired resources. For water extraction from C-type asteroids, the optical mining technique mentioned earlier is promising. Another approach involves enclosing the asteroid or a portion of it in a bag. then heating it to sublimate the ice directly to vapor, which is then collected and condensed. This baking bag method could be particularly effective for smaller asteroids that can be entirely enveloped. For metallic asteroids, different techniques are needed. Traditional mining methods, drilling, blasting, excavating, don't work well in microgravity where there's no weight to hold equipment in place and debris doesn't fall, but instead floats away. One proposed method uses magnetic fields to separate ferrous metals from other materials. Another involves using powerful lasers or electron beams to vaporize material, which is then collected and condensed. 3D printing technology could process raw asteroid material directly into useful products, eliminating the need to return raw materials to Earth or a space station for processing. The legal framework for asteroid mining is still evolving. The Outer Space Treaty of 1967, signed by all spacefaring nations, states that no nation can claim sovereignty over celestial bodies, but it doesn't explicitly address resource extraction. The Moon Agreement of 1979 attempted to declare space resources the common heritage of mankind, but no major spacefaring nation has ratified it. In 2015, the United States passed the Commercial Space Launch Competitiveness Act, which grants US citizens rights to resources they extract from asteroids. Luxembourg followed with similar legislation in 2017, positioning itself as a hub for space mining companies. Japan, the United Arab Emirates, and other countries have enacted or are considering similar laws. The Artemis Accords, signed by over 30 countries as of 2025, establish principles for resource extraction that allow companies to own what they extract while requiring them to share scientific data. But legal ownership is just one issue. There are also questions about environmental protection. Should we preserve some asteroids as scientific or cultural heritage sites? How do we prevent conflicts over valuable asteroids? What happens if mining activities inadvertently change an asteroid's orbit, potentially creating a collision hazard? These questions will need international cooperation to resolve. Several companies have already been founded to pursue asteroid mining, though the industry is still in its infancy. Planetary Resources, founded in 2012 with backing from Google executives and other investors, aim to identify and eventually mine near-Earth asteroids, but ceased operations in 2018 after funding dried up. Deep Space Industries, founded in 2013, was acquired by Bradford Space in 2019 and pivoted to providing spacecraft technology. New companies continue to enter the field with different approaches. Some focus on prospecting, identifying and characterizing potentially valuable asteroids. Others are developing the extraction technology. Still others are working on the infrastructure needed to support mining operations, communication systems, refueling depots, processing facilities. The industry is following a pattern similar to terrestrial mining, where different companies specialize in exploration, extraction, processing, and transportation. Government space agencies are also contributing to asteroid mining development, though often indirectly. NASA's OSIRIS-REx and Japan's Hayabusa missions, while primarily scientific, demonstrated technologies crucial for mining: precision navigation around small bodies, sample collection, and return to Earth. The Psyche mission will study what may be an exposed planetary core, providing data valuable for future mining of metallic asteroids. NASA's Asteroid Redirect mission, though cancelled, would have demonstrated capturing and moving a small asteroid, a technique that could be used to bring valuable asteroids closer to Earth for easier extraction. The timeline for commercial asteroid mining depends on both technological and economic factors. Most experts believe the first commercial extraction of asteroid resources will happen in the 2030s, focusing on water for satellite refueling. This initial market could be worth billions of dollars annually and would provide the revenue stream needed to develop more advanced extraction techniques. By the 2040s, we might see the first extraction of metals for use in space construction. The development of large space stations, lunar bases, or Mars colonies will create demand for construction materials that would be prohibitively expensive to launch from Earth. A single large space habitat might require thousands of tons of structural material. At current launch costs, that's tens of billions of dollars just for the raw materials. Asteroid-derived materials could reduce this cost by an order of magnitude or more. The 2050s could see the beginning of large-scale resource extraction, with multiple companies operating dozens of mining spacecraft throughout the inner solar system. Some asteroids might be moved to more convenient orbits. Small asteroids could be captured and brought to Earth-Moon Lagrange points, where they could be processed more easily. Larger asteroids might have permanent mining installations, essentially space-based towns dedicated to resource extraction. Looking further ahead, asteroid resources could enable projects currently in the realm of science fiction. Space-based solar power stations beaming clean energy to Earth via microwave become economically feasible when the construction materials don't need to be launched from Earth. Massive space habitats, like O'Neill cylinders housing millions of people, could be built from asteroid materials. Interstellar spacecraft, requiring enormous amounts of propellant and radiation shielding, could be constructed and fueled entirely from space resources. The environmental implications of asteroid mining are complex. On one hand, moving heavy industry and resource extraction off Earth could help preserve our planet's environment. Instead of strip mining Earth for rare Earth elements, we could get them from asteroids, where there are no ecosystems to damage. The carbon footprint of asteroid mining, once the infrastructure is in place, could be essentially zero. Solar power is abundant in space, and there are no greenhouse gas emissions in vacuum. On the other hand, we must be careful not to simply export our environmental problems to space. While asteroids don't have ecosystems to protect, they are scientifically valuable. Each asteroid is a time capsule from the early solar system, and destroying them for resources means losing that scientific information forever. There's also the risk of creating debris that could pose hazards to spacecraft, or worse, inadvertently sending an asteroid on a collision course with Earth. The social and economic impacts of asteroid mining could be profound. The influx of space resources could cause massive disruption to Earth's economy. If platinum group metals become abundant, industries that depend on their scarcity would need to adapt. Countries whose economies depend on resource extraction might find their primary exports devalued. On the positive side, abundant resources could enable new technologies and improve quality of life globally. Cheap platinum could make fuel cells economically viable for widespread use, helping address climate change. Abundant rare earth elements could make advanced electronics cheaper and more accessible. Asteroid mining could also drive the development of space settlements. Mining operations will need workers, and while initial operations will likely be robotic, human presence will eventually be necessary for maintenance, decision-making, and handling unexpected situations. These workers will need habitats, life support systems, and recreational facilities. Over time, temporary mining camps could evolve into permanent settlements, much as mining towns developed during Earth's gold rushes. The technology developed for asteroid mining will have applications beyond resource extraction. Precision navigation around small bodies is useful for planetary defense, deflecting potentially hazardous asteroids. Resource extraction techniques could be adapted for in-situ resource utilization on the Moon and Mars. The closed-loop life support systems needed for asteroid mining operations would be valuable for any long-duration space mission. International cooperation will be crucial for asteroid mining to succeed. No single nation has all the necessary technology and resources. The United States has advanced spacecraft and robotics. Japan has experience with asteroid sample return. Europe has expertise in precision navigation and landing. China is rapidly developing space capabilities, and other nations bring their own strengths. Collaborative efforts, sharing both costs and benefits, could accelerate development while reducing the risk of conflict over space resources. The educational and inspirational value of asteroid mining shouldn't be underestimated. The challenge of extracting resources from asteroids will require innovations in robotics, artificial intelligence, materials science, and many other fields. Universities are already offering courses in space resources, and students are choosing careers in aerospace engineering inspired by the possibility of asteroid mining. The idea that humanity could become a spacefaring civilization, no longer confined to a single planet, captures imaginations and drives innovation. As we stand on the brink of this new era, it's worth reflecting on the profound shift asteroid mining represents. For all of human history, we've been confined to the resources of a single planet. Wars have been fought over oil, gold, water, and land. But asteroids offer essentially limitless resources. There's enough material in the asteroid belt to support a population of trillions. The challenge isn't scarcity, but developing the technology to access and use these resources. The most fascinating individual asteroids. Among the hundreds of thousands of known asteroids, some stand out as particularly remarkable. Worlds that challenge our understanding, surprise us with their properties, or capture our imagination with their stories. These individual asteroids, each unique in its own way, remind us that we're not dealing with a uniform collection of space rocks, but rather a diverse population of small worlds, each with its own history, composition, and mysteries waiting to be unravelled. Let's begin with 2001 CB, an asteroid that shouldn't exist according to our conventional understanding of solar system dynamics. This small body, only about 1 kilometre in diameter, has an orbit unlike any other known asteroid. It travels from just inside Mercury's orbit to beyond Neptune, a journey that takes it across the entire solar system. With an orbital eccentricity of 0.99, its path is almost a straight line rather than the ellipse we expect from celestial bodies. How such an orbit came to be remains a mystery. Some scientists suggest it might be an extinct comet that lost its volatile materials, while others propose it could have been gravitationally scattered from the outer solar system. Whatever its origin, 2001 CB reminds us that the solar system still holds surprises. Vesta, which we've mentioned before, deserves special attention as the only intact protoplanet accessible to our observations. When Dawn's spacecraft arrived at Vesta, it revealed a world that had started down the path to becoming a planet 4.5 billion years ago, but stopped when Jupiter's gravity disrupted the asteroid belt. Vesta has a differentiated interior, an iron-nickel core about 220 kilometres in diameter, a rocky mantle, and a basaltic crust. This makes it a window into planetary formation, showing us what Earth might have looked like in its earliest stages. The surface of Vesta tells a violent history. The Rhea Silvia impact basin at the South Pole is 500 kilometres wide and 19 kilometres deep, with a central peak that rises 22 kilometres from the crater floor, one of the tallest mountains in the solar system. The impact that created Rhea Silvia excavated about 1% of Vesta's total mass, scattering fragments across the solar system. Many of these fragments have fallen to Earth as head meteorites, making Vesta one of only a handful of solar system bodies from which we have samples. But Rhea Silvia wasn't the first giant impact Vesta suffered. Beneath it lies the older Venonea Basin, 400 kilometers across. These two overlapping giant impacts created a complex landscape of ridges, grooves, and scarps that wrap around Vesta's equator. The Divalia fossae, grooves up to 15 kilometers wide and 465 kilometers long, formed when the impacts fractured Vesta's interior. That Vesta survived these catastrophic events intact speaks to the strength of its differentiated structure. 216 Cleopatra is one of the most unusually shaped asteroids known. A 217-kilometre-long body that looks remarkably like a dog bone or dumbbell. Radar observations reveal it to be a contact binary, two lobes connected by a thick neck, spinning once every 5.4 hours. But Cleopatra's surprises don't end with its shape. It has two tiny moons, Alex Helios and Cleo Selene, each about 5 kilometers in diameter, orbiting the spinning dog bone like cosmic fleas. The formation of Cleopatra and its moons likely involved a complex history of collisions and gravitational interactions. The asteroid appears to be a rubble pile, loosely consolidated material barely held together by gravity. Its rapid rotation creates significant stress. Cleopatra is spinning almost fast enough to fly apart. The moons may have formed from material ejected from Cleopatra's surface by its rapid rotation or by impacts. The whole system is a delicate gravitational ballet that has somehow remained stable for millions of years. 2014 JO25 revealed an unexpected property when it passed close to Earth in April 2017. Radar observations showed that this 1-kilometre asteroid has an extremely high radar reflectivity, about twice as bright as typical asteroids. This suggests its surface might be covered with metallic material, or possibly water ice, though at its distance from the Sun, exposed ice should sublimate quickly. The asteroid's peanut shape and slow 4-hour rotation were expected, but its unusual surface properties remain unexplained. 162173 Ryugu, visited by Japan's Hayabusa 2 mission, surprised scientists with its perfectly symmetrical spinning top shape and extremely dark surface, reflecting only about 2% of sunlight. But the biggest surprise came from its low density, only about 1.2 grams per cubic centimetre, suggesting it's more than 50% empty space. Ryugu is essentially a cosmic rubble pile, a collection of boulders and rocks held together by weak gravity. The surface of Ryugu tells a story of a violent past and ongoing evolution. Large boulders, some as big as buildings, are scattered across the surface. Many contain bright inclusions that might be altered minerals from ancient water interactions. The equatorial ridge that gives Ryugu its spinning top shape likely formed as the asteroid's rotation rate increased, causing material to migrate toward the equator. This process may still be ongoing. Ryugu's rotation is gradually speeding up due to the Yorp effect. 101955 Bennu, target of NASA's OSIRIS-REx mission, proved to be one of the most surprising asteroids ever studied. Like Ryugu, it has a spinning top shape with an equatorial ridge, but Bennu held secrets that only revealed themselves after months of observation. The spacecraft detected particles being ejected from Bennu's surface. The asteroid was actively throwing pieces of itself into space. These ejection events, occurring every few days, launched particles ranging from millimeters to centimeters in size. Some particles escaped Bennu's weak gravity entirely, while others went into temporary orbit before falling back to the surface. The cause appears to be thermal fracturing. Rocks on Bennu's surface experience temperature swings of over 100 degrees Celsius between day and night, causing them to crack and occasionally explosively fragment. This makes Bennu an active asteroid, blurring the line between asteroids and comets. 3200 Phaethon is perhaps the most comet-like asteroid known. despite showing no evidence of ice. This 5-kilometre asteroid is the parent body of the Geminid meteor shower, one of the most spectacular annual meteor displays. But how can a rocky asteroid produce a meteor shower? Something typically associated with icy comets. Phaethon has an unusual orbit that brings it closer to the Sun than any other named asteroid, just 0.14 astronomical units at perihelion, well inside Mercury's orbit. At this distance, its surface temperature exceeds 700 degrees Celsius. This extreme heating may cause thermal fracturing or decomposition of surface minerals, releasing dust particles that form the Geminid stream. Recent observations have detected a small dust tail when Phaethon is near the Sun, confirming it's actively shedding material despite lacking ice. 2002 MN is Earth's newest quasi-satellite, following a horseshoe orbit relative to our planet. From Earth's perspective, this 50-metre asteroid appears to orbit Earth, though it's actually orbiting the Sun in a 1-to-1 resonance with Earth. It approaches Earth, slows down and falls behind, then catches up again, tracing a horseshoe pattern that repeats every year. This orbital dance will continue for about 600 years before gravitational perturbations send 2002 MN onto a different path. 2.4. Themis made headlines when astronomers detected water ice on its surface, the first confirmed detection of surface ice on an asteroid. This was unexpected because at Themis's distance from the Sun, exposed ice should sublimate within years to decades. The ice appears to be replenished from subsurface reservoirs, possibly exposed by small impacts. Even more intriguingly, Themis also shows evidence of organic molecules on its surface, making it a particularly interesting target for understanding the delivery of water and organics to the early Earth. 9.0 Antiope is one of the most genuinely double asteroids known. Not a primary with a small moon, but two nearly equal-sized bodies orbiting their common centre of mass. Each component is about 85 kilometres in diameter, separated by about 170 kilometres. They orbit each other every 16.5 hours, tidally locked, so the same faces always point toward each other. The system likely formed when a parent asteroid was gently pulled apart by rotational forces or a glancing impact, with the two halves remaining gravitationally bound. 617 Patroclus and its companion Mennoetius form another true binary system, but these asteroids are Jupiter Trojans, orbiting at Jupiter's L5 Lagrange point. The two components, each about 100 kilometres in diameter, have very low densities, suggesting they're ice-rich bodies from the outer solar system. NASA's Lucy mission will visit this binary system in 2033, providing our first close-up look at a Trojan asteroid pair. 2867 Steins, visited by ESA's Rosetta spacecraft, revealed itself to be a diamond-shaped asteroid with a giant crater that removed much of its southern hemisphere. The crater, named Diamond, is so large relative to Steins's 5-kilometre size that the impact nearly shattered the asteroid. The survival of Steins after such a catastrophic impact provides insights into asteroid strength and structure. 2013 TV135 holds the record for the fastest rotating large asteroid, spinning once every 2.25 hours. This 200-metre asteroid is rotating at nearly the maximum rate possible for a rubble pile. Any faster, and it would fly apart. The rapid rotation has likely caused it to shed material from its equator, possibly creating a debris disk or small moons, though none have been detected yet. 1998 OR2 stunned astronomers when radar observations revealed it has at least two moons. The primary asteroid is about 2.5 kilometres in diameter, while the moons are about 1 kilometre and 0.5 kilometres across. This is one of the few known triple asteroid systems,
and understanding how such systems form and remain stable is an active area of research. 2008 TC3 holds the distinction of being the first asteroid discovered before it hit Earth. Detected on October 6, 2008, calculations quickly showed it would impact Earth's atmosphere over Sudan about 19 hours later. Astronomers worldwide tracked the asteroid during its final approach, and it entered the atmosphere exactly as predicted, exploding over the Nubian desert. Expeditions to the impact area recovered hundreds of meteorite fragments, designated Alma-Ata Sitta, providing the first opportunity to link telescope observations of an asteroid with laboratory analysis of its fragments. 4179. Toutatis has one of the most chaotic rotations in the solar system. This 4.5-kilometre asteroid doesn't spin around a single axis, but instead tumbles in a complex pattern that combines rotation around two different axes with periods of 5.4 and 7.3 days. This creates a never-repeating pattern where the same face almost never points in the same direction twice. The chaotic rotation likely resulted from a past collision or close planetary encounter. 2014MO was another asteroid observed before Earth impact, detected on January 2, 2014, and impacting Earth's atmosphere over the Atlantic Ocean 21 hours later. While only about 3 meters in diameter and completely burning up in the atmosphere, its detection demonstrated our improving ability to find even small asteroids on their final approach to Earth. 101955. Bennu deserves another mention for one of its most remarkable features, a boulder nicknamed Ben that stands 16 stories tall and weighs about 12 million kilograms. This house-sized rock sitting on Bennu's surface is so large that it has its own gravitational influence on the spacecraft orbiting above. How such enormous boulders ended up on such a small asteroid remains a puzzle. They may be fragments from Bennu's parent body, preserved for billions of years. 5261. Eureka is the first Mars-Trojan asteroid discovered, orbiting at Mars's L5 Lagrange point. Its spectrum matches that of A-type asteroids, which are extremely rare and thought to have formed very close to the Sun. How Eureka ended up as a Mars-Trojan is unknown. It may have been captured during planetary migration in the early solar system or represent a unique composition that formed in place. 2 Pallas, the third most massive asteroid, remains one of the most mysterious large asteroids because its highly inclined orbit makes it difficult to reach with spacecraft. Hubble Space Telescope observations suggest it has a somewhat flattened shape and may have a large impact basin near its south pole, but details remain elusive. Pallas appears to be a B-type asteroid, possibly containing water ice and organic compounds, making it a valuable target for future exploration. 623 Chimera is notable for having one of the longest rotation periods of any asteroid. It takes over 1,400 hours, or about 59 days, to complete one rotation. This incredibly slow spin might result from yaw perfect evolution or past collisions that nearly stopped its rotation. Such slow rotators are valuable for studying how asteroids respond to thermal forces over long timescales. These individual asteroids, each with their unique characteristics and stories, remind us that the asteroid population is far from homogeneous. Each one is a world unto itself, shaped by billions of years of collisions, thermal evolution, and gravitational interactions. Some preserve pristine material from the solar system's formation, while others have been processed and reprocessed through impacts and heating. Some are solid rocks, others are barely held together rubble piles, and still others may harbour subsurface ice or even liquid water.